Hello, hello. We are live. How's everybody doing? Getting ready to do our second Typescript AlgoKit workshop ever. AlgoKit 3.0 workshop. Our fifth workshop of the past couple of weeks. Looking forward to teaching with you all. Got 40 people in the live storm. I'll give folks just a moment to connect before we jump in. Hello, hello. Feel free to introduce yourselves in the chat. Oh, I can be louder. I can be louder. Welcome, welcome. Got Chris in the chat. Pakistan, good stuff. Argentina, very nice. California, Spain. Hopefully your power back is back on and stays on in Spain. Hello from France. Bonjour. Colorado, Lebanon. Wow, all over. Amazing. Georgia. We've been scheduling these workshops at different times of the day to try to be accessible to people in all regions, depending on when they're available. And yet we have learned that even if we schedule workshops at a certain time, we get global participants almost every single workshop. It's really amazing. People on in the morning, people on at, the middle of the night. Awesome. All right, we're going to jump in. So my name is Brian Whippo. I'm the head of developer relations here at the Algorand Foundation, and I'm excited to share with you all our AlgoKit 3.0 workshop. This will be a 4-hour, essentially an introductory workshop that goes through at the beginning, basic Algorand fundamentals, and then ramps up pretty quickly through building stuff on Algorand in code, and will be in TypeScript code during this workshop, and into smart contract development, and all the way through smart contract testing. And we've got some additional resources for you at the end. This is a new format that we're excited to share in this compressed way. And at the end, we'll have a survey to get some feedback from you all as we iterate and look to improve how we teach AlgoKit and get people from zero to knowing how to interact with the Algorand chain in code. So hopefully this will be fun and engaging, relatively swift, but don't hesitate to ask questions. We have a Q&A section in Livestorm. You can see in the bottom right corner, there's a questions button. Feel free to ask questions as we go, and we'll do our best to answer those both verbally and in text. And you can use the chat as we go along as well. And when we get to the end, we'll invite folks up on stage. If you have verbal questions, we can chat through stuff. And I'm pleased to introduce my co-instructor here, Gabe, Gabe.algo, and the two of us will be teaching you here today. So without further ado, I'll hand it over to Gabe.
All right, thank you for the introduction, Brian. Yeah, so as Brian mentioned, we are going to be monitoring the chat. We have our colleagues Joran and Chris in the chat as well. So as we go through the content, don't hesitate to be inquisitive, ask questions, and we'll do our best to answer them either in chat, or I'll kind of try and take a look and see if someone asks a questions that's relevant to the content. I'll answer it right then and there. I think to start, let me take you through the agenda and some of the learning objectives. Give me just a second here to share my screen. Let's see. Okay, I believe my screen is showing. Is that correct? Can I maybe get a quick thumbs up or acknowledgement in the chat? Looking good. Okay, cool. All right, so the agenda for this workshop, the first thing we're going to cover are some conceptual fundamentals of the Algorand blockchain. So we'll be talking through some of the core features that are good to know. as we go through the workshop. We're going to be building on these concepts and then implementing them in code. So in this workshop, we're going to teach you how to deploy smart contracts, how to create accounts, how to send and receive algo, how to create assets, and we'll be going through both the conceptuals of that, and we'll be actually implementing them together in code. The second section will be, I think Brian will be doing that. We'll just be working through some code examples, like I mentioned, how to create accounts, how to send assets, etc. The third section will be smart contract development. So I'm going to talk through some of the basics about smart contract development, how to deploy them, how to store stuff on the smart contract, how to write some of the business logic, and we'll actually also be taking a look at a code example. So we'll be sort of coding through a smart contract together, deploying it and interacting with it. And then the fourth section is smart contract testing. So we will be looking at both integration and unit tests. We'll explain sort of the difference between the two. And yeah, that will be sort of the workshop. We'll top it off. We'll cap it off with some additional resources and stuff you can use to continue your learning. And that'll be it. Next thing, let's talk about some of the learning objectives. So one of the main things we want you to get away from this course is to understand some of the blockchain fundamentals and its core economic principles. We are going to teach you how to interact with the blockchain using AlgoKit Utils, which is an open source library that makes it easy to interact with the Algorand blockchain. We are going to teach you how to read and write Algorand smart contracts in both, well, for this workshop in TypeScript, but last week we had a Python workshop, but this workshop will be focused on TypeScript development. We will teach you how to implement testing, deployment, and interactions for smart contract applications. And like I mentioned in the previous slide, we will share some additional resources so that you can continue your learning, and we'll also point you towards a digital marketplace app, which is sort of a full stack production ready application that has both a smart contract and a front end that lets you, it's basically like a fully featured marketplace application. Okay, so that's it for the learning objectives. We have some common, frequently asked questions. I'll go through these here briefly. And actually, before I continue, am I coming through clear? I just realized I normally have my AirPods in, but I'm using my laptop microphone. Am I?
Pretty good.
Hear me pretty good? Should I put in my, I might try putting in my iPods if it's not clear.
It sounds okay to me.
Okay. Okay, cool. Awesome. All right, so first question. Can I view a recording and get a copy of the slides? And the answer is yes. We're going to email that to you after the workshop. What are the differences between the Python and the TypeScript workshop? So all of the content is basically the same. The only difference is the code. So if you want to attend both, or if you've already attended both, we'll be going through all of the content in the same way. It's just that the actual code examples will be either in Python or TypeScript. Obviously today we're doing TypeScript. Another question is, will you run this workshop once? And no, we've already done several sessions, and I think we'll probably do more sessions throughout the year. And I think we're also looking to do sort of like a pre-recorded version of this workshop, almost like kind of like a Udemy style course that you can sort of watch on your own time. So kind of teasing that a little bit. Can I get support as a new developer on Algorand? And yes, absolutely you can. We would encourage you to join our Discord. That's probably the best way to get help. We have a dedicated Algorand channel on our Discord. We also have like a little help thread system where you can basically write like almost like a forum post with detailed information about your problem. And the team and the community are really good about answering questions there. So that'll definitely be a good place to start. Final question is, when I installed AlgoKit, the package version is not 3.x.x. So Some of you may have seen that we recently released AlgoKit version 3. That's just sort of a general term for all of the latest tooling. AlgoKit, as we'll see in the next few slides, refers to a broad set of tools that allow you to develop on the Algorand blockchain. But the actual CLI, the command line interface for AlgoKit that lets you instantiate projects and really get started developing, is on version 2.6.2. So if you run AlgoKit -- version, so if you open up a terminal and run AlgoKit -- version, it should show 2.6.2, and that is the latest version. So if that's what you see, you're all set. Okay, now we have a poll. The question is, what describes your reason for joining this workshop? I think we just want to get a sense of where everyone's at. I don't know if we have that poll ready, Brian.
Did it pop?
Let's see, I didn't see it pop up on my window, but maybe that's because we didn't set it to mandatory.
Oh,
so okay. So the polls, we'll try and fix that in the future, but usually they should pop up on your screen. Oh, there you go. Now it popped up.
fixed
Nice.
it.
Good job. Awesome. Okay, I'll give you guys a few seconds to answer the poll. We're curious where you're coming from. Have you built on Algorand before? Is this your first time? Are you new? Are you not sure? Are you just listening in? Wow, looks like we're pretty chain agnostic. Looks like most of you want to build on any blockchain. Oh, that's interesting. Okay. Well, hopefully as we go through this course, you'll get exposed to some of the features that actually make Algorand very convenient and easy to work on. I find it to have probably some of the best, if not the best, developer experience in Web3, but as we go through this course and you start learning how to build an Algorand and other blockchains, you can be the judge of that and let us know. All right, next slide. Which best describes your familiarity with blockchain and Algorand development? So if this poll does not pop up on your screen, you can go to the polls tab on the bottom right. Oh, there it is. Perfect. Cool. Looks like a good portion of you are beginners. That's great. This workshop is definitely geared towards beginners, so we're not going to leave anyone behind. We're going to explain everything from the basics and kind of take you from zero to hero, if you will, from not knowing too much about Algorand and how to develop on it to actually deploying a fully functioning smart contract. Okay, final question, I believe, is have you already installed AlgoKit on your local development machine? So I believe you were sent instructions on how to get AlgoKit started. We don't have too much time during this workshop to sort of debug individual issues, but there is a feature on GitHub called Code Spaces where if you did not have a chance to get AlgoKit installed on your machine locally, you can still use a code space to sort of bootstrap a virtual environment in your browser. And I can probably show you really quickly how to do that once we get over to the AlgoKit stuff.
Hello.
Hello? Did you say something, Brian?
All good.
Oh, okay, cool. Okay, so let's, I see a question from Owais Mansour. Sorry if I mispronounced your name. And the answer is yes, we will be providing a recorded version of this workshop and we'll email it to you probably, I think, usually an hour or two after this workshop completes. Okay, so let's dive into our first section, Algorand fundamentals. So we're going to be talking about some of the basic features that you need to know to get started developing on Algorand. And the first important feature on Algorand are what are called Algorand Standard Assets, or ASAs. And what ASAs let you do is they allow you to create on-chain assets. So if you wanted to represent any sort of financial instrument or any sort of digital asset, like a stable coin or in-game points or loyalty points, or even assets that are one-to-one, for example, property deeds, or what's another example? Well, we'll stick with property deeds for now. You can represent that on the blockchain. And what's cool about it is that it's a primitive on the chain. So there's no special coding involved to create an ASA on the blockchain. It's a feature that ships with Algorand. And the ASAs inherit the same features and security as the blockchain itself. So when you create an ASA and you send it to other accounts, it will actually double check to make sure that you're not double spending or that you're sending to the correct account, and all those sort of security features come pre-shipped, as it were. Let's talk about some of the basic features of Algorand standard assets. So, as I mentioned, they're built into the Algorand protocol. On some other chains, you have to, in order to sort of create these sort of assets, you have to code it manually. On Ethereum, for example, you're coding what's called an ERC20 smart contract. But on Algorand, it's a primitive. It's built into the chain. The code is really simple. And later on, during Brian's section, when we jump into some of the code, you'll see that it's actually quite simple to create and deploy these ASAs. It's literally just like a few lines of code. ASAs can both be fungible and non-fungible. So essentially, you can have a numerator and a denominator. Some of you are probably familiar with the concept of non-fungible tokens or NFTs. But essentially, a non-fungible ASA is just an ASA that's one-to-one. So a property deed would be an example of a non-fungible ASA that you could deploy on the network. And a fungible ASA would be an example of like a stable coin. You can also set optional manager addresses that allow you to update some of the fields on the asset. You can set the reserve address, which allows you to specify the amount of reserve in the case of a stablecoin, for example, or you can freeze the asset in place, or you can claw it back. And these are all optional. Asset creation increases the minimum balance by 0.1 algo. So in order to create an ASA, you have to increase the balance on your account by 0.1 algo. And that's called the minimum balance requirement. That's something that we'll talk about a little bit further down the road. And finally, to receive an ASA, you have to opt into the asset. So on other blockchains, you may have noticed, like if you sign up for a new account on Ethereum, one of the first things that happens to you is you get spammed by all of these sort of like random tokens. On Algorand, that doesn't happen because you have to opt into the ASA ahead of time. So it's kind of like a nice security feature. It's especially useful for companies that want to have accounting requirements, and if their accounts are being spanned by all of these like random ASAs, that actually causes like a big regulatory headache for them. But that is called the opt-in requirement. Okay, next up we have a quiz. Which of the following statements about ASAs is true?
I think we have the inverse. Sorry.
Okay, which of the following is not true about ASAs? So the options are: 1, you don't need a smart contract to create an ASA. The receiver of an ASA must opt into the ASA. You can create all kinds of tokens from non-fungible tokens or from fungible tokens to NFTs. and it costs 0.1 algo to transfer an ASA. This might be kind of a tricky one because I'm not sure if we explicitly covered this. But we definitely covered everything that's true here. Let's see. So what is not true about ASAs? So it looks like the top answer is that you don't need a smart contract to create an ASA. So that actually is, I'm getting confused on the double negatives here, but that actually is true. You do not need a smart contract to create an ASA. It is a primitive feature. It is a primitive or a layer 1 feature of the blockchain. So you don't have to custom code a smart contract or anything like that. So there might be some confusion here because I asked the question and then the slide is saying one thing and the question is saying another. But actually the correct answer is that what is not true is that it costs 0.1 algo to transfer an ASA. In fact, the transaction fee, which we'll cover in more detail, I think in the next section, is 0.001 algo, not 0.1 algo. So that was kind of, we confused you a little bit, but sorry about that. Okay, another core feature of the Algorand blockchain are transactions. So transactions are essentially cryptographically signed instructions that modify the Algorand blockchain's state. So transactions can cover a broad array of different interactions or different things you can, or different ways you can interact with the blockchain. It doesn't include just sending and receiving algo or assets. It actually also includes several things like interacting with a smart contract on the blockchain, or calling a method on that smart contract, or creating an ASA or modifying that ASA. It's really just any kind of transaction that modifies the state of the blockchain. And here are a list of the 8 different transaction types. So the most common one is obviously a payment transaction. A payment transaction just lets you send and receive algo, which is the blockchain's native currency. You can send it from one account to another. You can send it to a smart contracts account. And another transaction type is an asset configuration or asset config transaction. And this interaction just lets you create an asset or an ASA, which we discussed earlier. It lets you modify certain parameters of an asset or even destroy it. The third transaction type is an asset transfer, which enables you to opt into transfer or revoke assets. So an asset transfer is really similar to a payment transaction type, except with a payment transaction type, you're dealing with the native token algo, and with an asset transfer, you're just sending and receiving ASAs. Then there is an asset freeze transaction, which allows you to designate a freeze address to control whether a specific account can transfer or receive a particular asset. So what that means is I can create an ASA, and then if I created that ASA and I specify that I'm the manager of that ASA, I can send it to another account. And if this ASA has maybe some sort of requirement before that account can send it to someone else, like maybe it's a highly regulated token where you have to complete some paperwork or pay a tax or something before you can send it to someone else, I, as the creator and manager of the asset, can freeze that asset in place in your account, which basically prevents you from sending it to someone else. So I could, wait until you've done whatever thing you need to do, like, sign some paperwork maybe. And once you've done so, I can unfreeze the asset, and then you'd be free to transfer the asset as you will. Another transaction type is an app call. So application calls essentially just let you interact with smart contracts that have been deployed to the blockchain. As we go through the workshop, we'll be creating a smart contract that has various methods on it, and we'll be doing app call transactions to interact with those methods. And finally, the key registration, state proof, and heartbeat transactions. Those are outside of the scope of this workshop. We won't be touching those here, but they are related to the consensus on the blockchain. So a key registration transaction, for example, lets you register your account as online, which just means that I would like to put my algo as stake on the network and participate in consensus. And then there are state proofs and heartbeats. State proofs just occur periodically to secure the history of the blockchain so that it can't be tampered with. And then heartbeat transactions are just sort of these like regular transactions that your node on the network sends out to say like, hey, I'm still alive, I'm still participating. All right, another key feature of transactions are atomic transaction groups. So what atomic groups let you do is you can essentially just group several transactions together. You can group up to 16 of them into one group. And if one of them fails, then all of them fails. And in reverse, or conversely, if one of them succeeds, then all of them succeed. So atomic transactions are a really useful way for bundling transactions together that sort of depend upon each other. So if you have like a cascading series of transactions, like let's say if account B or account A needs to ascend to account B, and then account B needs to take those funds and pass it on to account C. And if each of those transactions rely on each other, you can group them together and you can ensure that they either all succeed or they all fail. All right. A common question we've been getting in the workshop is, how do Algorand transactions fail? So probably, the most common one you'll see as you're developing on Algorand is that, maybe you didn't set the correct receiver or sender, or maybe you don't have enough funds in your account to cover the fee. Just basically like user error type things where you didn't configure the transaction correctly. That's probably what you'll see the most. But the protocol itself also has various checks that it runs before a transaction succeeds. It'll ensure that you're not double spending, for example, that you've met the required fee, etc. So those are some of the reasons that transactions typically fail. All right, we have a quiz. The question is, which of the following statements is true about atomic transaction groups in Algorand? Okay, so which of the following is true about atomic groups? 1, a maximum of 8 transactions can be grouped together. Some transactions in a group can succeed while others fail. Up to 16 transactions can be executed simultaneously with all succeeding or failing. And finally, each transaction in an atomic group must pay its own transaction fee. Yeah, so I think most of you got the correct answer. So you can execute up to 16 transactions. And really the key piece of atomic groups is that they all succeed or fail. So we got like 65%. Got the right answer. That's pretty good. Okay, let's move on. Oh, I do see some questions in the chat. Screen recording. Yes, we are recording this session and we'll email it to you after the session. And yes, ASA stands for Algorand Standard Assets. So assets are just, or ASAs are just otherwise known as tokens. They just let you represent digital assets on chain. Okay, let's talk about fees and minimum balances. So the first thing that you have to know about sending and receiving on the Algorand blockchain is that you have to pay a fee. So anytime you want to send algo to another account, you have to pay a fee. And that's obviously because doing so requires computational resources. So if sending and receiving stuff, or just sending algo on the blockchain were completely free, then people could just sort of spam the network, and it would, cause a lot of problems. So there is a 0.0001 algo fee that's required whenever you send algo to another account. Another sort of anti-spam measure on Algorand is called the minimum balance requirement. So essentially, when you want to take certain actions on the blockchain, if you want to do things like create an ASA, or if you want to deploy a smart contract, or if you want to open up storage on the smart contract so that you can actually store data on the smart contract, we require a minimum balance requirement. So what that means is you just have to deposit a certain amount in order to take that action. Typically, the minimum balance requirement is 0.1 algo. So what that means is if I want to deploy an ASA, or a smart contract, I would just have to deposit 0.1 algo into my account. And it's important to note that that's not a cost. So it doesn't work like fees where you have to pay the fee and then you never get the fee back. The minimum balance requirement is actually just a deposit. So once you create the contract, you put the 0.1 algo deposit in your account. If you destroy the contract, then you can receive that 0.1 algo back, so you can actually use it again. It's not frozen in place in your account, if that kind of makes sense. All right, here's just some high-level information on fees and minimum balances. So as I mentioned, the fee for a transaction on Algorand is 0.001 algo. And there's also an opcode limit. I don't think I've mentioned this before, but essentially every smart contract has an opcode budget. So whenever you want to execute logic that costs computational resources on the blockchain, you have to you incur an opcode cost. So every smart contract deployed on Algorand has an opcode budget of 700, I think. Yeah, it's 700. And when you want to do something that's computationally intensive, like if you want to do a mathematical operation, like adding multiple numbers together, that will typically cost an opcode of 1. And then more computationally intensive operations like hashing data will cost, I think, anywhere from like 20 to 50, maybe more opcode. I can't remember off the top of my head how much it costs. But the idea is that the logic within your smart contract, each sort of operation costs opcode. So you'll have to ensure that you stay within that 700 opcode limit. And finally, when the chain is operating normally, like when it's not congested and everything is fine, the standard fee is 0.001 algo. But if the chain becomes congested for whatever reason, there will actually be like a dynamic calculation for the fee. And the formula for that is here, but essentially there is like a static fee that you have to pay, and whichever one is the greater of the two is the one you have to pay. But essentially what this formula means is that you have to pay per byte length. So the more bytes or the bigger that your transaction is, the more that you have to pay in fees. And that's only if the network is congested. Otherwise, you're just paying the standard 0.001 algo fee. Okay, quiz time. What is the standard? Oh, sorry. What is the
standard? Got to hear you that time.
So the question is, what is the standard transaction fee on Algorand during normal conditions? So the options are 0.01 algo, 0.001 algo, 1 algo. I will say 1 algo, that'd be quite expensive. Or the fee varies based on transaction type. All right, I have a feeling most of you guys are going to get this one. This one's an easy one. Yes, all right, good job. Looks like pretty much everyone got the correct answer. The standard fee is 0.001 algo. The fee definitely does not vary based on transaction type. It's always the same. The only time that it would vary is, as we discussed, if the network becomes congested, and then you have to pay based on the byte length of the transaction. Okay, good job, everyone. All right, here's just a bit more examples or a bit more information on fees and minimum balances. So you can kind of see here on this chart, here's an icon that represents an account, and this account wants to create an ASA. So before creating that ASA, it has to make sure that it deposits 0.1 algo in its own account. And then same goes for an opt-in. So like we mentioned before is you have to opt into an ASA before receiving it, and that also costs 0.1 algo. Or if you want to create an app, that also has a minimum balance requirement of 0.1 algo. Or if you want to sort of expand storage on your smart contract, you can also deposit more algo to unlock that. And probably the key thing to remember is that if you let's say opt out of the ASA, or if you destroy the ASA that you created, that minimum balance requirement disappears, so you can sort of get your algo back. All right, another quiz. So question is, what is the minimum balance requirement for a wallet that is an activated account, has created 2 ASAs, and has opted into 5 ASAs? Okay, so I think the trick to answering this question correctly is to just remember what the minimum balance fee is typically, and then you just have to kind of sum these up together. I am going to give you a very strong hint because we didn't explicitly mention this, but in order to activate an account on the network, so in order to create an account and then have it be listed on the ledger, on the blockchain, that actually also costs 0.1 algo. So the MBR for activating an account is 0.1. And let's see if you guys can piece it together from there. Looks like we're kind of split on this one. Most of you so far have the correct answer. So the correct answer is 0.8 algo. So essentially the way you derive that is each of these actions costs 0.1 algo, or has an MBR of 0.1 algo. And we're doing 8 different things. We're creating the account or activating the account. We're creating 2 ASAs, so that's 3. And then we're opting into 5 ASAs. So that's a total of 8 different things that we're doing. And each of those actions costs or requires a minimum balance of 0.1. So the correct answer is 0.8 algo. Okay, let's talk about AlgoKit. So AlgoKit is an open source suite of tools that let you develop on the Algorand blockchain. It basically includes everything that you need in order to develop on the Algorand blockchain from end to end. In this workshop, we're going to be looking at a few of them, not all of them, but I think most of them. We're definitely going to show you everything you need to know to, make some basic interactions on the blockchain, and as well as writing and deploying smart contracts. So this is a TypeScript workshop. So we'll be taking a look at Algorand TypeScript, which is just a way of writing smart contracts using native TypeScript. We'll also show you how to use LoRa, which is basically a blockchain explorer and visualizer. It's actually super neat. You can look at all of the transactions that you create on chain with your code, but you can also interact with the smart contract that you deploy. So it's a great way to sort of test your smart contracts as you're developing them. There's also the AlgoKit CLI, which essentially lets you bootstrap a project it lets you bootstrap like a workspace where you can build smart contracts, deploy them, and we'll be doing that here shortly. Then there's Utils, which we'll be using in the next section, and that just lets you create ASAs, create accounts. It's a great library for just interacting with the blockchain in general. I'll go through the rest of here fairly briefly, but Subscriber is a library that lets you just watch on-chain events. So some of you might be familiar with the concept of a blockchain watcher. That's where you just want to watch events on chain and react to them for whatever your use case may be. And Subscriber is just a really neat library that kind of sets it all up for you and makes it really simple. We have a VS Code setup for you as well with an AlgoKit. So when you're bootstrapping the project, it kind of comes configured with some nice defaults for VS Code and kind of like a workspace setup. I'll show you how that works. We also have a few starter templates. So if you want to just build and deploy a smart contract, we have a template for that. Or if you want to build a smart contract and have a front end for it where you can interact with it through a browser, we have a template for that as well. And then the CLI comes with this bootstrap command, which just means you can generate the project and then run this bootstrap command, and it installs all the dependencies for you so that everything is ready to go. And we also have a testing framework. So one of the coolest things about developing on Algorand is that it ships with a what's called LocalNet. And LocalNet is basically just a local version of the blockchain that runs on your computer. So it lets you see everything that you do. Like if you're, deploying a smart contract to LocalNet or creating an account on LocalNet, you can see that all locally on your computer. And you can also like speed it up and slow it down if you have logic that, depends on time. It's just a much more easier and flexible way of developing. And we also have unit testing and integration testing that we're going to run you through in this workshop. We'll just show you how to test your smart contracts. We have a visual debugger called AVM Debugger. There's actually also a VS Code extension where you can like visually debug your smart contracts. That's very cool. And then we also have a testnet dispenser. So on mainnet, you obviously have to pay like real money to get algo. But on testnet, which is like the test version of mainnet, you can use a dispenser to get as much algo as you need to do whatever you need, whether you need to cover fees to send and receive algo, or if you need to meet minimum balance requirements to deploy a contract, you can go to the testnet dispenser and get all the algo that you need. And finally, we have the deploy functionality with an AlgoKit. What this means is we just have various commands and tools that you can run to deploy your smart contract to various environments. So you can write your smart contract in one go, and then you can deploy it to mainnet, testnet, or localnet. And AlgoKit makes it really easy to do that. And we also have some CI/CD templates for like production grade stuff. So once you're ready to go into production with your project, you can run just a bunch of CI/CD tools, like tests, for example, in the cloud. Okay, now let's get ready to code. Sorry, Brian. In this section, we're kind of initializing an AlgoKit template. Is that right?
Yeah, I think we can do the init now, and then we'll take a short break. And then after the break, we will actually start running some code.
Okay, awesome. All right, well, I'm going to pull up my terminal here, and I'm going to show you guys how to initialize a AlgoKit template. Let me just get outside of screen sharing mode here. Okay, so if you have AlgoKit running on your machine, feel free to open up a terminal and follow along here. Let me make this a little bit bigger. Shout if this is too small. It looks pretty good on my screen, but if anyone thinks I should make it a little bit bigger, just let me know. So as I mentioned in the beginning of the workshop, if you do AlgoKit -- version, you should see that your version is 2.6.2. So that is the latest version. And if you run, let me just clear this out. If you run AlgoKit, or let me cd into my desktop actually. So I'm in my desktop now. If I run the command algokit init, this is going to start the initialization project for a new AlgoKit project. The first thing it's going to do is it's going to ask me a few questions. The first one being, what kind of project do I want to build? In my case, I just want to build a smart contract, so I'm going to select that. I want to code the smart contract in TypeScript, so I'll select TypeScript here, and we'll give this a name. We'll just call this TS Workshop 2025. And now it's going to create a directory with that name. It also asks you like what you want to call the smart contract. We're just going to stick with the default here and call it Hello World. And finally, it's going to ask me if I want to do a starter or a production smart contract. I would recommend that you go with a production ready template, just because that includes some of the test files that we're going to cover later. So if you're following along, I would select production. And then finally, it's going to ask me if I want to bootstrap the project. So do I want to install all of the dependencies? And yes, I do want to do that. And this can typically take a couple of seconds. The Node package manager dependencies can be a bit slow. There it goes. So we'll wait for this to complete, and then I'll run you all through the sort of directory structure that it creates. Last and final question is, do we want to initialize a Git repository and perform an initial commit? Why not? Let's do that. Okay, so if I open up this TS workshop, I'm opening up in Cursor just because that's the IDE that I'm used to. However, Cursor is just a version of VS Code that has some built-in AI features. So if you are using VS Code, it should all look very similar. I lost my screen here. Just give me one moment. Okay, let me make this a little bit bigger for everyone so you can see. All right, so this is an AlgoKit project template that we just initialized. One of the cool things is that it comes with this workspaces feature. So if you open up this JSON file that's here at root, or actually I guess it's a .code-workspace file in the root directory, on VS Code, you can click that and then hit open workspace. And that is going to open this up as a VS Code workspace. And what that does is it just lets you see the root and the actual project in the Explorer menu like this. And it sets up two different terminal namespaces for you. So if I'm running commands in this terminal, that's going to be in the root of the project. And if I'm running commands in this terminal, it's going to be within that project subdirectory that it creates for you. But so we generated a smart contract, and that is here within this project directory. You can see here we have various files that are just basic configuration stuff. So we have the vtest config, which is configuration for testing. We have tsconfig, which sets up TypeScript stuff. Here is a package JSON, which has all of the dependencies for the project. But what we're probably most interested in is the actual smart contract itself. So you might remember that we initialized a Hello World smart contract, and that was created here. So we have a smart contract code here. This is a really simple hello world contract written in TypeScript. It has a method that takes a name as an argument and then returns this greeting that includes that name. And then there's also these files here that we'll cover in depth throughout the workshop later. Lets you test the smart contract, doing both unit tests and integration tests. And then we have this deploy-config file that lets you deploy the smart contract. And if you did follow along, it's important to run the bootstrap command. So I'm seeing some, so I'm seeing these red squigglies here because I did not build the contract. So if you do AlgoKit project build, that will actually build that smart contract. Oh, wait, no. Oh, sorry, the command is actually here, AlgoKit project run build. That will build the smart contract that we see here. And it creates all of these artifacts. So artifacts are just build files, essentially. So this is all of the build files that you need to deploy your smart contract on chain. Here we have like the actual TEAL, which is sort of the underlying language that the Algorand virtual machine understands. TypeScript is a next step up. It's like a superset of this language that lets you write smart contracts in a much friendlier way. But yeah, these are essentially just like build files that are created when you run that command. So if you were following along, make sure you run that AlgoKit project run build file, and then you'll have everything you need to know. And yeah, I think that's pretty much it. I think if anyone here has any questions, I'm taking a look at the chat briefly. I hope that was all clear. So yeah, just to recap, we went through some of the fundamentals of the Algorand blockchain, talked a little bit about all the tools within AlgoKit, and what we did just now is we initialized an AlgoKit template.
Round 2 of the AlgoKit 3.0 workshop experience. We're going to talk about Algorand building blocks in code. So I'm actually going to start with some slides before we get into the code. But the purpose of this section, which is a new section for our AlgoKit instruction, is to cover, on one hand, things you can do without smart contracts, right? There's all sorts of functionality that does not involve smart contracts. And that's really important. And we've gotten feedback over the past several months about how we were kind of getting into smart contracts too soon, too frequently. There's actually a lot you can do on Algorand without needing them. So this addresses a lot of that before we get to smart contracts in the third hour of this workshop. The other thing that this addresses is AlgoKit Utils. So since 2024, a couple of really big things have changed. One is that the AlgoKit Utils library has really matured, and its API has changed dramatically and has really gotten to the point where you almost never need to reach for the SDKs anymore, which we're at sort of a lower level of abstraction. But Utils is a more abstracted library with a more fluent interface. We'll see some of that in a moment. That will be the centerpiece of interacting with Algorand through TypeScript. And it's pretty new. And the other thing that I will say is, since 2024, actually since like earlier, I guess it was late 2024, the JavaScript SDK, which underlies the utils library that we're going to go through in this hour, changed substantially, and it was upgraded to a V3. And there are all sorts of typing changes, and that is essentially a mandatory upgrade because the older version of the JavaScript SDK is not going to be supported anymore. And so using utils sort of abstracts that away from you as a developer. You don't really need to worry about the underlying SDK, but as long as you're on utils V8 or later, then all of that is taken care of, and you'll have a very explicitly typed experience working with the chain with all sorts of autocomplete and IntelliSense in your development environment. Cool. So let's jump in. So in this hour, we're going to be using a script, a single file. We're going to step through 10 different things, sort of scaffold our way up through a set of Algorand conceptual building blocks, but we're going to do it in code and see the results and then visually inspect what we did. So we have a repo called the Algorand Typescript Workshop. And Gabe, if you could throw the link in the chat or in the link section, that would be great. And we're basically going to use this as our project for the remainder of the workshop. When you get that cloned, you can use AlgoKit Project Bootstrap All, like Gabe just showed us, and that'll install all the dependencies for the project. And we're going to be in the workshop script directory. So we'll get to that in a sec. Along the way, we're going to touch on a number of things. The first thing I want to introduce is AlgoKit LocalNet. This is a sandbox network. It runs in a Docker container on your local machine and enables you as a developer to very, very quickly get started talking to a network. You have access to all the funds because you've got the Genesis block that has all 10 billion algos, and it's really easy to reset it or fix it if you break it. So using a simple command, AlgoKit LocalNet reset completely wipes the network and starts a fresh one. And so you never really have to spend any time fussing around with setting up a sandbox or trying to get testnet algos to do stuff. You can do it all for free on LocalNet in seconds. We'll also be using LoRa, LoRa the Explorer. LoRa is an acronym that was sort of reverse engineered to be the live on-chain resource analyzer. And it's a free open source explorer developed by the foundation. It's not as fancy maybe as some other explorers, but it has a lot of developer features and visualizations, which we'll go through in this hour. It also lets you connect to KMD, the key management daemon, which is part of the Node software package on Algorand. And on LocalNet, you can create wallets and interact with them through KMD and also through LoRa. So as a developer, this is your hands-on tool for messing around on LocalNet. Along the way, we'll create transactions and groups and take a look at them and applications. And LoRa enables you to inspect chain data both through the node or AlgoD, but also historical data through the indexer, which is the Postgres database we'll talk about in a sec. And you can always get to LoRa at lora.algokit.io. You can also type in your command line AlgoKit explore LocalNet. Cool. So when you get into code in AlgoKit Utils, the single starting point for pretty much everything you're going to want to do is what we call the Algorand client. This is a stateful class that has a whole bunch of methods and properties on it. And virtually every line of code you write will start here in one shape or another. We got this for Python and TypeScript. Obviously, we're doing TypeScript today. And I will illustrate, and you'll have the opportunity to play around with this in just a moment. So in our code experience, we're going to create some transactions, a simple pay. This is the most basic Algorand transaction type. Then we're going to do a little asset configuration. So we're going to create a token, and that's achieved through an asset config transaction. You can set a bunch of fields that define the token and who has control to do things with it. Then we're going to do some stuff with the token. So we'll be opting into that token, which is a step that's required on Algorand before someone can receive the ASA, and transfer it around. So that's just a Another simple transaction to transfer an asset from one account to another, right? Still, no smart contracts involved. This is unlike the Ethereum virtual machine where contracts define a token. Here, you just have a native entry in the ledger of the global chain, and moving a balance of a token from one place to another is just an asset transfer transaction. And along the way, we'll be using two REST APIs. The first is through AlgoD. So this is the node. AlgoD actually performs the consensus protocol for Algorand and produces and verifies blocks, but it also has some endpoints that you can use to submit transactions and get the current state of the ledger. It doesn't really have much history. It only holds on to 1,000 rounds of history by default. If you want history, you would use another tool called the indexer. And the indexer basically partners with a node called a follower node, and it goes one block at a time, and it stores all the data about the transactions and other things into a Postgres database. And that is much more elaborately indexed, and you can do all sorts of searches against it. All right. Who's ready to see some code? Let's see some thumbs up in the chat. This is the point at which the rubber meets the road in this workshop. All right. So we're in VS Code now. Shout at me if that's not legible, but I've zoomed in quite a bit. I think that should be readable, but shout at me if not. So, for context, this is the Algorand TypeScript workshop project that you can clone, and it's got this personal bank smart contract, which we'll get to in the next hour. We're just in this folder down here called the workshop script. So this is all set up as a mono repo, and you can see how the workspace is defined in this Algorand TypeScript workshop.code workspace. And VS Code handles the folder hierarchy for you when you open the workspace. So we can ignore most of that for now. And we're just down here in a very simple directory, a workshop script, got a little package JSON. You can see we have one dependency. So this is all we're using. No other dependencies. And we've written a very simple script that will take you on a code tour of the things we just saw on the slides. There are 10 steps here. Step 1, initializing the Algorand client. Step 2, we're going to make some accounts. Step 3, we're going to send it that algo transaction. So Alice is going to pay Bob. Step 4, be creating an asset using an asset create method. Step 5, we're going to query one of those REST API endpoints from AlgoD to get the information about the ASA we just created. In step 6, Bob's going to opt into the ASA so he can receive it. Then in step 7, Alice sends Bob some of the token. In step 8, we'll query again AlgoD to get Bob's what we call account information, so that'll have all his holdings. And in step 9, we're going to take it up a notch, and we're going to send 2 transactions that are grouped together in an atomic transaction group, one of the cool features built into Algorand as a layer 1 primitive, so that the transactions succeed together or fail together, but they are inseparable once grouped. And finally, in step 10, we're going to use that indexer to do a transaction search, much like you would if you were doing a historical search of chain transactions. Cool. All right. So I'm going to go ahead and run this and let it go all the way through, and then we'll unpack what happened. Taking a slightly different approach than I did last week. I think this will make sense. So we're going to go, actually, it might make sense. No, I don't want to do that. We'll do it like this. Okay. So I mentioned that at the beginning, our entry point is we've got the Algorand Foundation / AlgoKit Utils library, and we import the Algorand client from it. So to create the client, the canonical way to do this is just to set Algorand equal to Algorand client dot whatever network you want to connect to. For development purposes, you would use localnet. We have a handy dandy little function called default localnet. So as long as you don't mess with any settings, this will just work, and you'll be able to interact with the localnet in all sorts of ways through this Algorand client class. Then we're going to make some accounts. So I mentioned a moment ago that the Algorand client class is stateful. So when you use these functions, Algorand.account.from environment, we're going to make an account called Alice. It then remembers that account. You can use it later, and I'll show you how that happens. So what's happening here is this is where we see what we call this like fluent chaining of methods. So if you do Algorand dot, you see a whole bunch of properties and methods exposed on the class. And this is your gateway into all the stuff that you can do. And we tried to organize it around key categories of actions. So in this case, we want to make some accounts. So we're going to do Algorand.account dot, and you have a whole bunch more methods. You can ensure an account is funded. You can create an account from a mnemonic. You can get an account from elsewhere. And there's probably 20 different methods here related to account management. So everything is sort of conceptually grouped on the properties of the Algorand client class. So in this case, we're using this from environment, and essentially the default behavior here is it will check if you've defined some account in your environment, but when we're on localnet, it does this. So it basically goes to the key management daemon on the node that's running within localnet in your Docker container on your laptop, and it makes a wallet using the name that you gave it. If it doesn't exist, it'll create it for you. And then that wallet and its account is available throughout whatever else you're doing. So this is kind of neat because if you need to have Alice do a bunch of stuff, this creates an Alice account deterministically. So as long as you're using the same localnet and the same Alice wallet, you've got the same account number throughout everything that you're doing. And it's kind of durable. Along the way here, we also pass a second parameter in here, and we're going to fund Alice's account with 100 algos. And you'll also see that there's a little helper here called algo, and you can pass it a number or a big int to define a quantity of algo. And AlgoKit Utils has a bunch of little helper classes like this to be very explicit about quantities and other things related to the chain that are sometimes nuanced. Cool. So we're going to create an Alice account, and we're going to create a Bob account, and then you can see them printed out here in the console log statements. So Alice got this account LADX, and Bob got an account RNX7, and they are funded. And what I've done throughout the script here is included a log that has a link to Laura. So let's take a look at Laura. Cool. So here's Laura. This is the account view, and you can see in the URL laura.algokit.io/localnet, so you know what network you're on, /account, and you know what you're looking at. And here's Alice's LADX account. I ran the script and a bunch of stuff happened, so she's got like 97 algos left. You can see the minimum balance, or MBR, that we were talking about earlier, how many assets she's got, and transactions that have occurred. And Laura fetches these from the chain, either live and very recently or historically. So this is sort of the simplest view of an account on the chain. Here's the assets, and we'll see how those get created in a moment. And then if she had created any smart contracts or opted into smart contracts that use storage on her account, those would appear down here. So throughout this hour, we'll be sort of bouncing back and forth between the code and Laura to see what do we do in the code and what does it look like when it's visualized in the Explorer. And then Bob's account is the same story, essentially. Cool. So I'll pause there before we get into step 3. Check for any questions. Chat looks good. Questions look good. All right. Shout at me if I'm going too fast or something doesn't make sense. I'm going to keep going. So let's do something with these accounts. Step 3. So here we're going to do a very basic transaction. Alice is going to pay Bob a couple of algos. So you'll see a pattern emerges here. Got our Algorand client. And this time we're going to do an Algorand.send because we're going to send a transaction. And when you do that, add another dot, and your IntelliSense will give you all kinds of options for what kind of transaction you want to send. Got app calls in here. We got asset related transactions in here. And in this case, we're just going to send a simple payment. So creating and sending a payment is essentially one fell swoop. And what's happening here is we're saying, all right, take my client, we're going to send, which means we're going to prepare a transaction and send it to the chain kind of all at once. There are ways to break this process down into smaller steps. And it's going to be a payment transaction. And then we give it some parameters. In this case, we just need to know a few things. The receiver and the amount are required. Everything else is optional. And I've added a note. Hi, Bob. So within this one-liner, we're taking our stateful class, connected to LocalNet. It's preparing a transaction. In this case, it's a payment with these parameters. And because the Algorand client class remembers the Alice account that we created with it, it is essentially handling having Alice sign this transaction because she's the sender of it. So it's all abstracted away. You don't have to worry about that. You don't have to build a transaction and sign it separately. You don't have to worry about where her keys are. The Algorand client handles all of this. And thus, we find this to be a really fast and smooth way to build on Algorand through the Utils library. That's it. In the console, we can see what happened. So when step 3 ran, we get a result back. So the transaction's created, signed by Alice, sent to the node, and confirmed by the node. And transactions on Algorand are defined by a unique transaction ID. In this case, we can visually examine the transaction in LoRa using a similar link like we did before. So this time, we're using LoRa to inspect a transaction. See the ID here, judge what kind it was, timestamp on the chain, what block was included in, the fee that was paid, and then how did that payment work, right? Alice was this LAD account, Bob was RNX, and she paid Bob 2 algos. Now we can see the note down here. LoRa has some helpful decoders, stuff on chain, so generally in base 64, so it's not human readable. So in many places, there are helpful decoders. You can actually read this stuff. Then my favorite part of LoRa is the transaction visualizer. So this graph here is very simple in this example, but we'll see a more complex one in a little while. Is a visual representation of what happened in this transaction group. In this case, it's just one transaction. And you see that Alice's account LAD was the first, Bob's account RNX was the second, and then you see a directional arrow, a payment of 2 algos from account 1 to account 2 in this transaction. So as groups of transactions get to be more complex, it can be hard to figure out what's going on in many block explorers. So we developed in LoRa this visual graph representation of transactions and groups to make it easy. You can also download these images and share them if you need to. And then the last thing I'll mention is LoRa exposes the raw JSON of the object that you're looking at. So this is what a transaction on Algorand looks like as JSON. So it's got the fee, it's in micro algos, the first round in which it was valid, the last round, who sent it. A few things that are not always relevant. The reward stuff was from a version of the protocol years ago. The Genesis hash identifies the network, and then the ID is the readable name of the network. In this case, DockerNet is localnet. Here's that unique ID I mentioned. The entry around offset is like where it sits in the block. This was the first transaction in the block, so it's 0. If you had 50,000 transactions in a block, which is a thing on Algorand, it could be much later in a very large block. Here's that note, space 64. Payment transaction, very simple. 2 million micro algos, which is equivalent to 2 algos, sent to RNX Bob's account. The close amount is like if you want to completely close an account off the ledger at the same time you send this transaction, you can optionally add that on there as well. So you could be like, send 2 algos to Bob and then the entire rest of my algo balance somewhere else. You can see the timestamp. It's like a Unix timestamp. And the signature. And this is where blockchain gets fun. So it is cryptographically signed. This signature is produced by Alice's private key, and it's checked against her account. This is not literally a public key. It's a human readable account number, but this has to match, and the node validates this when you submit a transaction. And you can see the type. It's pay. That's it. Cool. Back to the code. Let's do step 4. So we're going to ramp it up a little bit. In step 4, we're going to create a token. So here, again, Alice is going to do the token creating. We use our Algorand client, and this time we're going to send an asset create transaction. It takes a few more parameters compared to a pay. It's otherwise the same process. And the way this works is you'll need to give it a name and a unit name. Asset name is like human readable. Unit name is meant to be like a ticker. Neither of these are unique, or just for display purposes. And I'll show you what's unique in a minute. The total supply is in terms of the smallest unit of the asset. So in most cases, the asset is displayed with some number of decimal places. In this case, I've put 6 decimals on there. That's very similar to algos themselves. And so the way that this works is these would be decimals in the display of this quantity, and there would be 1 million sort of whole units of the asset. But on chain, everything is a uint64. And so you define things in terms of the smallest indivisible unit. And that would mean here, instead of having 1 million, we would actually have 1 trillion of the micro MFAs. And then we set some other settings. Default frozen is a global feature available on Algorand. So when you create an asset, it can just be frozen in people's accounts by default. It has to be moved around in special ways. Sometimes that's desirable in certain situations, could be by regulatory requirement. And then we have a set of roles. So Algorand provides role-based asset control, RBAC, in managing assets. Again, all of this is without smart contracts. It's just built into the protocol. So we set a manager who can essentially configure the asset after it's created, a reserve account that holds any supply that's not circulating, using air quotes. A freeze account is one that has the authority to freeze an asset's holdings in someone's account. And a clawback account. This is a special feature where if, let's say, Bob has a couple of units of this token in his account. It could be frozen there. Maybe there's some like court judgment against Bob and his assets have been frozen. And then Alice, in this case, has the authority to use clawback to move that asset to another account, even if it's frozen. So that's a pattern sometimes where you would create an asset, it would be default frozen, and then you would use the clawback capability to move the asset around through that authority rather than letting people freely transact in the asset. And a couple more things, we give it a URL. Note that this is immutable. Can't change this later. Could be anything. Here it's literally a web address. It could be data that links to other asset metadata. It could be an IPFS reference. It could be, some other string of bytes. You can use it in a number of ways, and we have standards on Algorand for how asset metadata can be attached to an ASA, but that's beyond the scope of this course. And then finally, a note. You can always put a note on a transaction. And so once we do that, the result that we get back has a bunch of information on it. So if you do dot, you can see get an asset ID. This is the unique identifier. It's a uint64 or a big int in TypeScript. So there's only ever one. And if you need to positively identify an asset, you would want to use its asset ID. The result also gives you confirmations of transaction or transactions, the group ID if there was a group, any return values, etc., and the IDs of those transactions. So all this stuff is available from the result just by doing a simple await Algorand send asset create. And then finally, after we create the asset, we can go check it out on LoRa. So in this case, we issued this transaction. We got asset 1010, and we can go check it out here. So here's LoRa's visualization of an asset. You see the name, the ticker, total supply. Note that this is 1 million, not 1 trillion, because it's already been formatted using the decimal configuration. It's not default frozen. There's that URL. And all of the accounts that play some role on the asset. You can also see that in JSON form. Basically the same thing, except some of this is in base 64. And you'll notice that LoRa exposes an opt-in button because you can connect your wallet to LoRa. In this case, we would use the KMD on LocalNet. And you can actually interact with stuff through LoRa. So more than just an explorer, that's a hands-on tool for development and creating arbitrary transactions. And if you ever just need to do something weird on the chain, you can use LoRa. All right, let's keep going. Step 5. So now that we've created an asset, let's get some of that info we just saw in LoRa through an API call in code. So in this case, we again are using our client, but this time we're using the asset property, and there's a whole bunch of capability underneath of that. So you can do asset dot, you can do bulk opt-ins or outs. You can get account information about that asset, or just get the asset information by its identifier. And that's what we're doing here, and just pass in that asset ID that we stored in a variable above. And then, oops. And then we'll basically get an API response back that's typed and lets us inspect it in various ways. Cool. So, oh, I killed my terminal. Oh well. We'll do it again. So remember I mentioned before, you can do AlgoKit localnet reset. Let's just take a second. Boom. So it tears down all these containers, create them anew, and done. Fresh network. So now, if I want to run the script again, boom. Oh no, it's not happy with me. I don't know why it's not happy with me. I don't know. Oh, I broke something. Sorry. My fault. Okay. Cool. We're back in action. Cool. So in code, if we want to look at an asset, we hit that AlgoD endpoint. In this case, it's v2/assets, and you give it the ID, and you get a nice typed object back. This time our ID was 1004. See all that stuff we just saw in LoRa, in name, in raw bytes, et cetera, all the roles that are set for that asset, etc. So very simple to interact with. We're going to keep going. So now that we have an asset, we know about it, let's get Bob involved. So here we're going to have Bob opt into this ASA so we can receive it. Same pattern, Algorand send, this time asset opt in. And we basically just need to give it two pieces of information. Who's sending this transaction? In this case, it's Bob. Our stateful client remembers Bob's account because we created Bob's account. And we pass in the asset ID that we're going to have Bob opt into. And you get a transaction confirmation back. And it looks like this. So asset opt-in, here's the TXN ID. And then you can check it out on LoRa. And here you go. So LoRa visualizes this as an asset transfer, but it adds the context that this is an opt-in. And this is basically just a zero quantity asset transfer to oneself. So Bob, his account is YVP since I reset the local net. He sends 0 to himself, and that has the effect of opting him into the asset. And if we take a look at his account, we'll actually see that he is, I already ran the whole script, but he's got the asset listed in his account asset holdings. Cool. So let's see what that looks like in code. Sorry, 2 more steps. So in step 7, we're actually going to send that token. Same thing, Algorand.send, but this time asset transfer. Sender's Alice, receiver's Bob. Pass in that asset ID, and we're going to pass in the amount of indivisible units. So remember, we had 6 decimal places on this. So I'm sending 3 million MFAs, but that's really like 3 in display units. And we've added a note, have a few of my first ASA. And you can see that down here as well. So we got the confirmation for the asset transfer, and we can see what that looks like on LoRa. So same thing here, little purple asset transfer lozenge tells us that that's what type of transaction it was. This time though, it was for 3 of the token, and our little visualizer shows what's going on. We transferred 3 units of MFA from Alice to Bob. There's that note. Cool. So let's see what Bob's account looks like after he receives this ASA. So we're going to take a look at the current ledger of the chain. And the way that we do that is we use a get information call. which hits an endpoint in AlgoD called v2 accounts, and you pass in the address. So very similar to what we did before to get the asset information, except this time we're under the account property of the Algorand client class, and we just do a little get information. So when we do that, we see a return object like this. So Bob's account information. And there's a lot going on here, so I'll just step through this real quick. The amount in the account info is the algo amount. So that's his balance on the chain. You see the minimum balance that's required. In this case, he's got an account and he's opted into one ASA. So his MBR is 0.2 algos, or 200,000 micro algos. You can ignore the pending rewards. It's an old thing we don't use anymore. The status refers to whether or not he is participating in consensus. So in this case, Bob is not running a node, so his status is offline. We can see what kind of stuff Bob has done on the chain. Has he opted into applications for data storage? Has he opted into assets? Yes, he's got one. Has he created any apps? No. Created any assets? No. If he had data stored in local storage with some smart contract, that would appear here. If he had created applications, that would appear here. And we see the assets array. So this is essentially what we were looking for. And he's got 3 million micro units of MFA ID 1004 not frozen in his account. And those are his asset holdings. If he had more, they would appear there. Auth address is if Bob had rekeyed his account to some other account. Created assets and apps, none. He's not incentive eligible because he's not even registered as online in consensus. I'm going to skip some of this stuff. And then you can see the actual public key in terms of bytes. Again, his algo balance. And then this tells you, as of round 6, this was Bob's account info. And then the last two properties there are related to consensus participation. So the last time Bob's account on a node sent a heartbeat or proposed a block. So those are tracked as part of the account state. We're almost there. So up to this point, we've created accounts, created an asset, opted into an asset, sent an asset. We inspected the asset. We also inspected an account information, including Bob's algo and token balances. And so we're going to step it up a little bit more now. So we learned earlier that you can send atomic transaction groups on Algorand. And the way to do this is to essentially create a new group when you're sending, and then you just chain together a bunch of methods to create whatever transactions that you want to include in the group. So this is fun in Utils. This is my favorite part of the library. So here we're doing a send. So we're going to prepare this stuff and send it all in one fell swoop. We're going to create a new group. And so we're explicitly saying, I'm going to group these things together. And then you just keep going, right? This is literally just one line of code, right? It's just formatted to look pretty. So we do add payment, a dot add payment. Give it the info just like we did before. Then we do a dot add asset transfer. Give it the params just like we did before. And then you can keep going if you want. Like I could add an app call. I could add an asset config. You can just keep chaining these things together until you get to the max, which would be 16 transactions. In this case, though, 2 is good enough for us. And we just run a dot send at the end. It composes the whole group. So it links the transactions together with a unique identifier called a group ID, and it sends them all off together and gets the result. And we can see what that looks like in the console down here. So in this case, the first transaction ID in the group, because there's multiple now, had this ID, and we can go check it out on LoRa. So this is just one transaction, but something has changed compared to the last time we saw a pay from Alice to Bob, which is that now we have a group ID. So let's drill into that. So now we start to see the fun part of LoRa, where a transaction group has, in this case, 2 transactions. It tells you how many of each type. And our visualizer gets more interesting because each of these is an individual transaction. And so the graph grows and it gets to be more interesting. In this case, we can see both the payment from Alice to Bob and a transfer of her first asset from Alice to Bob. all visualized. So I will take a moment just to see if I can pull up. I did not prepare this ahead of time, so this is all live. Let's look at a more complex group. Oh, here's an interesting one. So if we look at this transaction, this is another visualization. It's a smart contract transaction. There's a lot of stuff going on here. But you can see something pretty cool, which is that this one transaction also triggered 3 nested inner transactions that were all app calls. And you can see how the transaction visualization graph grows. And maybe there's another interesting one. I'm just literally hunting around. That one has a bunch of inners. Yeah, so some of these groups have lots of transactions, but you get to see them either visualized as a table or in a nice graph showing kind of who sent what to whom or who called which application and so forth. And the arrows can go in different directions. In this case, this account called the app, and then at the end, the app actually paid them back 0.001 algo. That's interesting. Cool. So almost there. The last thing that we do with our utils code is use our indexer. So the last few times we hit a REST endpoint, it was the AlgoD endpoint, which is the main node. But now in step 10, let's do a little historical searching. So we have a little bit of a delay built in here because the indexer on localnet can be a little bit slow sometimes, but you can pretty much ignore that. And to query the indexer's chain history, this time we go into our Algorand client class, and we're going to grab a client from it. So we go another level deep. So move that out of the way. So Algorand dot, and this time we're going to use this client property. You can see the docs that come up in here explain that you can get various Algo SDK clients or app clients. You can do all kinds of stuff. I'm going to go in and go do dot client and then dot, and look at all these options. So here we're going to get an indexer client in particular. In the smart contract section in the next hour, you'll see a little bit more about what you can do with app clients. But here we just need an indexer. And then on the indexer, you can see a bunch of things you can do. You can do all of these different kinds of lookups as well as searches. And in this case, we're going to do a search for transactions. And the search for transactions has a bunch of methods on it as well. And you can build your query based on different parameters. In this case, and again, we're all just chaining together method calls. This is functionally a one-liner to do all of this. So in this case, we're searching for transactions, dot asset ID, give it the asset ID for which we want to find transactions. And we say we want to look for asset transfers in particular. So I'm not interested in the create transactions. I'm interested in the transfer transactions of assets. And then slap a little .do on the end. And what we end up with is a response that has a bunch of transactions, and we want to create a little array of the IDs of those transactions we found and log them out. And here we are. So throughout the script, we did a few asset transfers, and our indexer search was able to find 3 different transactions on the chain from that indexer Postgres database. And that is the end of our script. So throughout, just to summarize, we imported the AlgoKit Utils library and used the crown jewel of the library, the Algorand client, to do basically everything here through fluent method chaining. So we pointed that client at localnet, we created accounts, sent a payment, created an asset. We queried some data from the chain called the AlgoD REST API. We opted into the assets and more transactions. We transferred an asset. We again hit AlgoD to get information about Bob's account. We did a more complex atomic transaction group with 2 transactions linked together. And then finally, we did a little searching through the index or database to find an array of transactions based on certain criteria. That's it. Cool. So let me take a look at the questions before we go into the break. I see some questions. Looks like Gabe has covered some of these. Yeah, interesting question from Jesco. Does LocalNet produce blocks even though there's no transactions issued? There's actually 2 modes. By default, LocalNet holds on the current block and waits for transactions. And then every time a transaction is sent, it prints a new block. However, you can also have it in regular mode where it just like churns out blocks every 2.7 seconds and continues to advance even if you're not transacting. Depending on your use case, you may want one mode or the other. If you're testing something that's based on time, you might want it to just run normally. But in most other cases, you would want what we call dev mode, where it just holds on the current block until another transaction is received. But it can print many blocks very, very quickly if you're running through tests, for example, and you need to send lots of transactions and not wait 2.7 seconds for them to be confirmed each time, and it will accelerate your testing. And I'll take a look at the Q&A. Okay, so Anupa has a question about manager reserve freeze clawback when it comes to ASAs. Good question. So when you create an asset, I don't know when that question was asked, so I may have covered a little bit of this, but the manager is whomever can configure the asset after it is created. If you want an asset to be completely immutable, maybe some NFT that is created once and can never be changed, you would actually zero out the manager address and you would set it to what we call the 0 address. And then no one can ever send a transaction for the 0 address, and the asset is effectively immutable and nothing can ever be changed. But if you have a manager address specified, then Alice can continue to configure that asset over time and modify the other addresses. The reserve is used for things like if you look at USDC, they have, they minted like, trillions of USDC, but it's not all actually circulating. So most of it sits in the reserve account waiting to be distributed to someone. That's a common use case. Freezing is often used for regulated assets that can't move on their own, and you've got to get permission from somebody to transact, and then somebody will come in and move the frozen asset essentially on your behalf. But freeze could also just be used in a situation where maybe a credential has been issued to someone and it's not transferable, and you want to make sure that the account that's got the credential can't just give it to somebody else. So that could be another use case. And then clawback, like I said, it could be used in a situation where something is frozen and it just needs to be moved through a clawback operation rather than the holder being able to transact on their own. Clawback can also be used for theft recovery. If you had something tokenized and it ended up in the wrong place through malicious activity, you could actually claw it back. And clawback can also be used for an asset that's controlled by a smart contract. And that's where the smart contract address would be here in this role. And the smart contract could effectively transfer that asset using clawback operations. And then you can get into things that can get pretty fancy. Cool. And how do you justify clawback in case of a fraud? I mean, that's really a legal question. The chain provides a generic set of capabilities that can be used in many, many different ways and composed together in even more ways. So in the relevant jurisdiction, right, I'm not a lawyer, but you would need to understand what the law is around the scenario that you are you're effectively operating through Algorand's technology. But the technology is agnostic to all of that. It's just a capability to move a asset holding from one account to another. whether it's being done to like literally claw back something that was stolen, or for some other use case, the protocol doesn't know anything about that. All right. So that brings us to the end of session 2, or hour 2. We're going to go ahead and take another 10-minute break. It's 3 minutes until the hour, so we will reconvene here at 7 past the hour. Gabe will take us through smart contracts. Thanks, everybody. See you in 10.
Okay, welcome back, everyone. I am going to give you all maybe a minute just to kind of gather. Hope you all enjoyed Brian's section. Did a little bit of hands-on coding and learned how to do some basic interactions on the chain, how to create accounts, how to create assets. We're going to be building on some of that knowledge and learning how to create and deploy smart contracts in this section. So just like the sections I did previously, we're going to cover some of the fundamentals of smart contracts, what they are, some of the things you can do with them, some of their core features, and a few things you really need to know. And then we're going to dive into some hands-on stuff. So we're going to take a look at a smart contract where you can deposit and withdraw algo. So it acts as kind of like your personal bank. And yeah, we'll step through some of that code, and I'll teach you guys how to build it and how to deploy it and how to interact with it on LoRa. Cool. So let's get started. Just checking chat really quick to see if we have any opening questions. Cool. Looks like we're all set. Yeah, a lot of questions around ASAs and clawbacks and freezes. Clawback is definitely something that you want to be very careful about setting. If you're launching like a meme token or something on the blockchain, you typically want to leave the clawback address undefined, because otherwise you can sort of rug people. That's really an option meant for tokens that are backed by companies or institutions that sort of have inherent trust behind them, and you're sort of trusting them to manage the token well. But okay, let's get started on Algorand smart contracts. So what are Algorand smart contracts? Essentially what they are is they're programs that can be deployed to the network. They let you, you can like write business logic using those programs, and you can write functions that people can call. So any sort of application or business logic that you want to have to be interactable on the blockchain, you would use Algorand smart contracts for that. So they are blockchain deployable programs that enable secure, scalable, and decentralized applications. And you can write them both in Algorand Typescript or Algorand Python. And as I mentioned a little bit earlier on, both Algorand Typescript and Algorand Python are a superset. So they're like a high-level language that allow you to write these programs in a language that is much easier to write in than the underlying language that it compiles to. So Algorand Typescript will actually compile into what is called TEAL, which stands for the Transaction Execution and Approval Language. And TEAL is sort of like an assembly-like language, really similar to assembly actually, that compiles further down into machine code, which the Algorand virtual machine can understand. And the Algorand virtual machine is sort of this process that runs on each node in the network that is constantly evaluating transactions, and is really the heart of the protocol's processing. And finally, smart contract code is updatable. So if you deploy a smart contract to the network and you decide later that something needs to be fixed or you want to add features, you can actually update that smart contract. And that is something that you have to determine ahead of time whether or not the smart contract is updatable, because otherwise you can also deploy smart contracts that cannot be updated. And that lets people know that they can, they can trust that the smart contract that you deployed can't be changed later on. So it's really sort of up to you to determine whether your smart contract should be updatable. One of the coolest features of Algorand applications or smart contracts are the fact that each one comes with an associated account. This account acts as sort of like an escrow for the application. So it can actually hold tokens, it can receive tokens, it can send tokens. So any business logic you have where you want to use the application's account, you can use this here. So it is important to note that the smart contract itself is not the account. It's a separate escrow account. So the actual resource on-chain for the application itself would be referenced using the application ID. In this case, you can see it's like 1, 2, 3, 4 as an example. And then it would have a separate account that's associated with the application that would have its own address. And so here the address is ABC123. And so you can kind of see here, like here we have some pseudocode for a smart contract application called Hello World. It has the same sort of Hello World method that ships when you initialize an AlgoKit project. And here it's kind of showing that the account is a separate component of the application that can hold its own algo and tokens, etc. And these application accounts act just like any other regular account on the blockchain. The only difference is that on a normal account, you're signing transactions using your own private key. So if you want to send algo from one account to another, you would sign that transaction and then submit it to the network. But with an application account, there is no signing process. It's really just the application logic itself that determines whether or not you'd send or receive from that account. So you would actually write logic here within this method to send algo, as an example, from the application account. And I'll pause here just to see if there's any questions on this section. Okay, it looks like we're good. Don't hesitate if any of this doesn't make sense or you want me to clarify, just drop it in chat and I'm happy to pause and expand on it. Okay, we have a quiz. True or false? An Algorand smart contract is an account with an account address as its unique identifier.
I'm looking for it.
All right, cool. I think I was checking over the poll questions earlier. I think we have this one.
Did it pop?
Yes.
Cool.
Okay, so most of you had, we're kind of going back and forth here, 50-50. So it looks like most of you are saying it's true. Is that true? I think what we're trying to emphasize in the previous section is that applications and accounts are really two separate resources on the network. So an application does have an account, but the application itself is not the actual account, if that's what it makes sense. The resource for the application is referenced by the application ID, and the associated account is referenced by its address, its account address. So I think I'm even a little bit confused by this question myself, but I think the answer is false. So the application itself is not the account. They are two separate but related concepts and resources on the network. Okay, next section. I see Anupa here said I was caught in action sharing Python references in a TS in a TypeScript session. I think, yeah, you must be talking about the code here. I think we're trying to make this like sort of agnostic pseudocode. Maybe some Python slipped in here. You might be right. Anyway, the next section that we're going to talk about is resource usage. So if you have a smart contract, for example, that needs to reference other resources on chain. So in this diagram right here, we have a smart contract with a method called getAssetBalance. And this method might have some logic where you're retrieving the balance of a given account. So I would call this method and I would get the balance of an account that I provide to it. And so what we're referencing here is the account itself as an on-chain resource, as well as the asset that we are getting the balance for. So if what I'm trying to say here is that you have to provide those resources ahead of time. So if I'm trying to get asset B's balance for account A, then I have to tell the smart contract ahead of time what asset ID it needs to know and what account address it needs to know. And that's just to keep the chain efficient. If we didn't require you to specify those resources ahead of time, there would obviously be some computation that would have to occur. So the network would have to find those resources on chain and then get the account balance. But if you provide it ahead of time, it just keeps everything nice and light and efficient. So smart contracts require explicit resource references. Typically, those resources are accounts, assets, applications, or boxes. Boxes are just a type of storage on chain, which I'll cover in the next section. You provide those references using what are called a reference array, which you can see right here. Usually what that means is you're just passing in like the account address or the asset ID in an array using code. I don't think we'll show you what that looks like in this code, but it's like really simple to do. And actually, AlgoKit Utils now does it for you automatically by default. So whenever you call an application method that has to look up certain resources, AlgoKit Utils behind the scenes will actually do sort of like a lookup call that will grab those references for you and then automatically populate them. So this is mostly abstracted away for you, but it's good to know that you have to supply those references ahead of time. Okay, actually, let me just check chat here really quick. See if we have any questions. Anoop has a question about the Puya compiler. Regardless of the high-level language used on top of it, is it natively inbuilt using Python, if I'm not mistaken? And yes, I think what you're asking is, what is the Puya compiler built in? And I believe it is written in Python. Correct me if I'm misunderstanding your question. I believe we are moving towards writing that compiler in a different implementation or a different language. But yeah, it's written in Python. But regardless, you're compiling both TypeScript or Python down into Teal. Okay, next section. Quiz. All right, everyone get ready for a quiz. Okay, when developing an Algorand smart contract to interact with an NFT, which reference array should be passed? Okay, so the options that we have is a boxes array, an assets array, an accounts array, or an app array. Let's see how you guys are doing on this one. Have 9 replies. Looks like most of you got this correct. So an NFT is a type of Algorand standard asset. And so you would have to supply the asset ID within the asset array when you're calling that smart contract. So ahead of time, you have to specify the asset ID because that's what the smart contract, that's the resource that the smart contract needs to have access to. Okay, let's talk about storage types for smart contracts. So there's a few different ways that you can store data on your smart contract. The three ways that you can store data are called global storage, local storage, or box storage. Global storage is basically just like universal or global storage for your smart contract. Global storage is meant for things that are like, supposed to be universally accessible. It's, data that's not specific to any user that's interacting with your blockchain, but it's just generally utilized by your smart contract logic. One thing to keep in mind is that there are some limitations. So global storage has a total storage capacity of 8 kilobytes, and you can store up to 64 key value pairs. So those 64 key value pairs can be a total of 8 kilobytes, and they're accessible to all users interacting with the application. Local storage is basically account-specific data. So if you have a smart contract where you want to store information on a per account basis, you would use local storage. Every time that an account opts into an application, you can create local storage for that particular account. The key difference between global storage and local storage that you have to keep in mind is that the user can actually clear out or delete their local storage or user-specific data. So you need to make sure that you can handle that. Obviously, if you had data in local storage that was vital to the overall business logic of your application, you'd have to be very careful if you're storing that in local storage, because the user could delete that and they could potentially break your application. So that's why you'd want to use global storage versus local storage. But local storage is great for data that isn't universally applicable to everyone. It's just data that needs to be used by a particular account interacting with that application. And like global storage, there are some limits to it. You can store up to 60 or 16 key value pairs, and those can have a total of 2 kilobytes. So basically, you have 2 kilobytes of data per user that you can store on the application. And then finally, we have box storage. Box storage is something we're going to be using in the smart contract that I will demo here shortly. Box storage it's just a catch-all method for storing data on your application. You can store up to 32 kilobytes per box, but you can actually add multiple boxes. So theoretically, you can store an infinite amount of data on-chain on your smart contract using box storage, but there is a minimum balance requirement that you have to meet in order to unlock storage on the application. So you're basically paying per byte that you are storing on-chain. And yeah, all storage types are affected by minimum balance requirements. Global and local storage charge different rates for integers versus byte slices. If you really want to go into detail on some of that stuff, I would encourage you to check out the documentation, which we'll link you to towards the end of this workshop. But we lay all that stuff out in detail there. Another really cool thing about smart contracts is that you can do what are called inner transactions. So in the same way that Brian walked you through creating assets and creating accounts and sending algo from accounts to other accounts and all those things, using AlgoKit Utils, you can actually do all of those things from a smart contract itself. So in this diagram here, we can see that we have this application smart contract, and then within the logic, we have these various methods. One of them lets you actually deploy an application. So you could do like this sort of factory pattern where you have an application that deploys other applications, which is really cool and opens up a lot of different use cases. You can obviously also send payments from the smart contract. So if you remember going back a few slides, we talked about how every application has its own account. Using inner transactions, you can actually send algo from that account to any other account on the network, including other application accounts. And you can also create assets from an application. So this combination of inner transactions opens up a lot of possibilities, like a lot of stuff you can do. For example, if you wanted to have like some sort of like custom logic that dictates how an asset is created, like who can create an asset, what sort of parameters the asset should be created with, that could all live inside of your smart contract logic. And then every time someone calls this create asset method, for an example, it would execute all of your logic and then it would actually create the asset on chain. Let me know if any of that isn't clear. I'm happy to cover that a little bit more detail. Looks like we're all good in the chat, so I assume that's making sense, which is great. I think we have another quiz. Cool. What capability do inner transactions provide to Algorand smart contracts? Okay, this one's kind of a layup, pretty simple one.
So maybe I can find it.
Yeah, if Brian can find it. I'll take a look here too, see if I can. You got it. Awesome. Okay, so we're asking, what do inner transactions provide to Algorand smart contracts? So what can you do with them, basically? Call another blockchain. So could you call Ethereum from an Algorand smart contract? That'd be interesting. Send transactions on behalf of the app account. Inner transactions are free to send. Or sends a transaction to itself. Okay, let's see how you guys are doing. Okay, so it seems we're pretty much universal. Have some consensus here. The correct answer is yes. It allows you to send transactions on behalf of the app account. So you can send algo or ASA or assets that are stored within the application account from the application's logic. Okay, moving on to the next section. Okay, here we have sort of like a project workflow diagram. This diagram is just sort of taking you through the development process of an Algorand smart contract. We would start over here with project initialization. We've already done some of this when we ran the AlgoKit init command, which scaffolded a project for us. It initialized the Algorand project structure, bootstrapped the environment, like installing dependencies and all that. And that's the place where you would start. The next portion would be obviously implementing your smart contract logic. That's where you would define all of your methods for the smart contract. So the different ways that people can interact with your smart contract. It's where you would define what sort of storage, if any, that your smart contract uses. It's basically just building out the logic of your smart contract. This term, ABI methods, I'll explain this really briefly. You're going to see this a lot as you're developing contracts. You're going to see terms like ABI. You're going to see the word ARC4 or ARC56. It's like don't overthink these terms. It's actually really simple. Basically, what ABI is, or what ARC56 or ARC4 lets you do, is it lets you specify an interface for your smart contract. And what that means is that people can know ahead of time what sort of methods your smart contract has available, how to call them, what sort of parameters to call them with, and it also lets you specify like what those methods return. So it's just a way of specifying ahead of time, or it's a way of allowing users to know how to interact with your smart contract. So once you've written your smart contract, you can build and generate the artifacts. So we did this really quickly when I was showing you how to bootstrap your own project. We ran the AlgoKit project run build command, and that just takes your TypeScript logic and then spits out all of these different artifacts that will be used to deploy the contract on chain. So you can kind of see here, we're going from Python TypeScript, we're going from the TypeScript contract logic, and we're creating these different artifacts, including the teal, which is the language that the Algorand virtual machine can understand. We're creating this arc56.json file, and that's basically, again, just going back to the interface that I talked about. This JSON file just has all the metadata about your contract. It lists all the various methods, how to call them. Also, like, has descriptions for the methods that you can include. And then it also creates this typed app client. So what this essentially is, it's a TypeScript client that you can use both within your backend or front-end code as sort of an entry point to call your smart contract. So once we go on to deploying our own smart contract and looking at some of the code, we'll see that after we build the smart contract, we generate this client that exposes all of the methods that we can run on the smart contract itself, and also has a few other helper methods like a deploy method, which we'll actually be calling. And so this basically just creates a really neat way for you to interact with your smart contract. It creates a client that you can use to interact with your smart contract, both on the front end and the back end. And it all has all the types built in. So it's just a really nice, easy, and clean way of interacting with your smart contract throughout your code. And so once we built and deployed the smart contract, or just built the contract actually, we'll test it. So in the section after this, we'll go into detail about unit tests and integration tests, just making sure that everything on your smart contract runs the way it's supposed to before you deploy it to the network. So yeah, the deploy step is kind of self-explanatory. You're taking these build artifacts, namely the teal, and you're pushing it to the network so that your application is live on chain. And then finally, we can use LoRa to interact with the smart contract that we deployed, and we'll be doing that together today. Or you can also use a front end. So you can use this sort of you can use this open source library called useWallet that lets you connect all of the various wallets available in the ecosystem and then interact with your smart contract. You can also use AlgoKit Utils to interact with the smart contract directly, but we'll just be using LoRa. Okay, so these steps right here, I would honestly just ignore them. It walks you through generating like a blank smart contract in a newly initialized AlgoKit project. But since we have the smart contract already built for you in the code that you cloned to run through Brian's section, I would probably just start there. So if you're following along and you have that project already ready, that's where we'll start. Otherwise, you can go to the bottom right and go to the links tab, and we should have a link there that takes you to this repo, which you can clone, and it'll have the smart contract that we're going to take a look at ready for you here in this projects directory called Personal Bank. So let me just pause here briefly, see if there's any questions that you guys have. Looks like we're all set. Cool. Brian's got everyone covered. That's great. Okay, so in this section, let's look at an actual live contract. I am going to walk you through some of the code of the contract. I'm going to show you how to build it, and then we're going to deploy it, and then we're going to look at it on LoRa, and we're going to interact with it. So hopefully by now you've had a chance to clone this repo, which this is the same repo that Brian was working on that had the scripts, these workshop scripts. There is another directory in the projects folder here called personal bank, and that's where our smart contract lives. Let me just get rid of this terminal here so it's a bit easier to see. Do you guys mind giving me a thumbs up on the size if this looks good? This is big enough, easy to read. Looks pretty good on my screen. All right, cool, perfect. Okay. So the smart contract that we're going to take a look at is called Personal Bank. And basically what it lets you do is it lets you deposit a certain amount of algo to the contract's account, and then it lets you withdraw that algo as well. So to follow along here, the smart contract logic is within this contract.algo.ts file, which is within the project subdirectory called Personal Bank. So if I go into the personal-bank directory and I go to this smart contracts directory and then click into the personal_bank directory, I will see this contract.algo file. And this is where the TypeScript logic of our smart contract lives. Once we build it, you'll see that it spits out all of these artifacts. So again, these are the files that are built from your TypeScript logic. And these are really the files that are used to deploy the contract on chain. But I'll show you a little bit more what that looks like once we actually build the project. So to start off with, let's just take a look at what some of this code looks like. So every TypeScript smart contract starts off with this import statement where we're importing various classes and utilities from this Algorand-TypeScript namespace. Here we're importing things like boxmap, and boxmap just lets me initialize box storage on the smart contract. We're importing things like this TXN class, which lets you read transactions or just manipulate and interact with transactions. We're importing some types. So one of the fundamental types on every smart contract is either bytes or uint64, but we also have types on top of that are built on top of those, like account, and yeah, so we're just importing all of the tools that we need here to build the smart contract. Then we're defining the class. Every TypeScript smart contract is basically just a TypeScript class where you're writing you're adding different members and methods to the class. And so we have this personal bank smart contract. It extends the base contract class. So every smart contract in TypeScript is going to extend this base contract. And here we have two methods. So these are the two methods that we can use to interact with this contract once we deploy it. The first method that we have is this deposit method. So the deposit method just lets you deposit funds into the quote unquote personal bank. So the account that we're actually depositing to is the applications account. It takes a pay transaction as a parameter. So when you're calling this deposit method, you're going to be calling the method and supplying it with a actual transaction that is a payment transaction that pays the Algorand or the application's account with the amount that you want to deposit. And then the withdraw method just lets you withdraw whatever amount you deposited. So when I deposit, let's say 100 algo, I can then call this withdraw method, and then I just get that 100 algo that's in the application's account sent back to my own personal account. So that's the high-level features of this contract. Let's take a look into some of the logic here and see what that looks like. This ABI method decorator, again, you could almost just consider this boilerplate. Pretty much any method that you want other users to interact with, you decorate it with this ABI method decorator, and that just tells the compiler that, hey, this method needs to be publicly accessible, so we need to generate all of the available metadata for it, so that we can create those interfaces that allow users to know ahead of time what methods are available on the contract and how to call them, etc. Okay, so when we call this deposit method on chain, the first thing that it's going to do is it's going to run this assert statement. So it's going to look at the payment transaction that we supply along with the method call, and it's going to ensure that the receiver of the payment transaction is equal to the application's address. So this global variable that we import here basically lets us access a bunch of different things. We can get the creator address. We could get the group ID if this method was called with a group transaction. We can get the minimum transaction fee. We can get the opcode budget. If you remember back in the fundamental sections, we talked about opcode budgets, how basically every time you do some sort of computation on the smart contract, you consume part of the budget. So here you can actually access this variable to make sure that you're staying within that budget. But all we're doing here is we're just referencing the application's address, and we're making sure that the deposit that we're sending is going to be going to that application's address. And then here's another assert statement where we're just making sure that the amount that we're depositing is greater than 0. And then here, once we pass those asserts, we're defining a couple of variables. Just for convenience, we're saving the deposit amount in this deposit amount variable, which is going to be referenced later. And in this variable, we are just checking to see if the user or the account that is calling this deposit function has already deposited any amount to the contract's bank. So the way we access that is we're looking at the box storage of the contract. We're seeing if an entry already exists. If so, it's true. So that means that the user would have already deposited. Otherwise, it's going to be their first deposit, and we'll handle that a little bit differently. But actually here, I should back up a little bit. I did not talk about the box storage that we're initializing this contract with. So this contract uses box storage, and we're defining that ahead of time. So when this contract gets built and deployed, it's going to allocate this depositor's box storage to its storage. And this is what lets us keep track of who's deposited what. So this box map helper just lets you use box storage in a way that you can define basically key and value pairs. So what we're doing here is we're just setting up box storage that lets us store the amount that the user deposits keyed off by their account, right? So we're just storing the deposit amounts for each depositor, with the key being the depositor's account address, and the value is the amount that they deposited. And that's why further down here, within Algorand and Typescript, you can use these sort of like control flow statements. So in the same way that you're used to, writing if statements or switch statements or any sort of like control flow logic, you can write that using the same native Algorand TypeScript syntax here within the contract. So here we're just seeing if they've already deposited. So if they've already deposited an amount and set up a key within the box storage, then we're just going to add that deposit amount to their key within the box storage, right? So we have this box storage. We're looking it up by the pay transactions sender, and then we're adding that amount to the value. Otherwise, if this is their first time depositing to the contract, then we're just initializing the value with the amount that they initially deposited. And then finally, when you call this deposit method, we're just returning the deposit amount. So if I deposit 100 algo for the first time, it's going to just return 100 to let me know that that's my current state within the box storage. Okay, I'm going to check chat here really quick, see if this is making sense. If you guys have any questions as we're going along, like definitely don't hesitate. Like I said, I'm happy to kind of slow this down or explain more. Brian, I hear that you unmuted. Did you want to say something, or was that an accident?
I was just going to say, Noop and I have been chatting for a while, but none of it is directly pertinent to what you've been doing.
Okay, no, that's great. That's awesome. Yeah, if you guys do have questions, you're totally good. It's no problem. I'm glad to see a lively chat. That's always a good thing. Okay, cool. Let's move on quickly to the withdraw method. So this method lets us deposit algo to the application's account, and then to withdraw it, we would call this withdraw method. And let's step through the logic here really quickly. So the withdraw method lets you withdraw all funds from the sender's account. So if I deposited 100 algo, I would call this withdraw method to get the 100 algo back to my account. What it does is it transfers the entire balance of the sender's account back to them and resets their balance to 0. Obviously, the sender must have deposited in order to withdraw, and it returns the amount that is withdrawn after you call the method. I do want to just sidetrack here a little bit and show you guys that these descriptions that you're writing here, which describe the methods, are generated in these artifact files. So if we look at this artifact, this arc56.json file, we can actually see that it's looking at those descriptions that we wrote for the deposit method, for example, and it's including them here. So for here we have the name of the deposit method, and here we have the arguments that that deposit method can be called with, including the actual description of that argument, as well as here we have the high-level description for the deposit method itself. So that's just to say that these sort of JS doc strings that you're writing here are included in the artifact files that are then later used to annotate these methods, so that when you look at them in LoRa, for example, you know exactly what this method does, including its descriptions, parameters, etc. Okay, so really briefly, what this withdraw method does is it just looks at the box storage and it sees if you have, if you've already deposited something, and looks at how much you've deposited. If you haven't deposited anything, this assert statement would fail. Basically, it would say like no deposits found for this account, and then it would exit out of this method entirely. But if you have deposited, then it would set up this inner transaction, which is just a payment from the application's account to the account that you're calling it with, right? So this transaction.sender is looking at the transaction that you call this method with. The sender would be you because you're the one calling it, and then it's sending back the deposit amount, and we're setting the fee to 0 here, which basically just means that the fee is paid by the caller. I won't go into this too much, but basically this prevents people from being able to drain your application's account. I can probably follow up with this if someone asks a question in chat. And then we're just returning the amount that we deposited. So that's pretty much what the smart contract logic looks like. I think we have about 8 minutes left here, so we can see if we can, first of all, build this contract. So if I open up my terminal and I go into the CLI for the personal bank subdirectory or project directory, and I type AlgoKit project run build, that is going to take my Typescript files and generate all of those artifacts that we need to deploy the project. Looks like that executed successfully. So now I can run AlgoKit project deploy. And if I specify localnet, then that's going to deploy this smart contract to localnet. So if I hit enter, formatting here is not ideal. Let me see if I can fix that. Okay, that looks a little bit better. Sorry, I had to make this a bit smaller, but you can see here that we successfully deployed this application to localnet, and it gives us the name, the ID of the application. We're going to go ahead and copy that value because we're going to use that to look it up on LoRa. It also tells us the address that it was deployed from, or no, sorry, this tells us the address of the application's account. So this is like the bank of the account of the application. And this tells us the address that the application was deployed from. And I won't cover this too much, but just for background and context, when I run this deploy command, what's happening is it's looking at this deploy-config Typescript file, and it's basically just running it. So it's setting up the client for the smart contract, and then it's running this deploy method, and then it's funding it. You can probably just take a look at this on your own time. It's really nicely annotated with comments that explains everything that's happening. But just so you know, under the hood, when I'm deploying it, it's running this script here. But yeah, going back to the contract we've deployed, if I copy this application ID, and if I type AlgoKit Explore, this should bring up LoRa. So we can look up the application that we just deployed by its ID. See if it's there. Here you can see that the application's been deployed to the network. Here's all the information. So Brian kind of stepped through how to look at resources on chain using LoRa, but like, you know, this is the application that we deployed. Here's the ID. Here's the address that created the application. Here's the address of the account associated with the application. And you can also take a look at like box storage and the global state. And here you have like a table that shows the history of transactions associated with that application. So like here we can see this transaction ID starting with JGR. This is the actual application call that we made to deploy this application. But what's cool about LoRa is you can go over to the App Lab. And if you create, you can create an app interface. So if you hit this create button and you type in the application ID of the contract that you just deployed and hit this use existing button, what you can do is you can provide that arc56.json file that I talked about that has all of the methods and their descriptions and parameters. So if I go and reveal this in Finder, go back to LoRa, and if I drop this arc56.json file in here, this is going to create an interface for my smart contract so that I can actually interact with it using LoRa. So I'm going to call this Personal Bank 2 since I already made one. Okay, so now if I go back to LoRa's page with that application ID, you might see this new ABI methods section. Oh, I lost track of the chat. Let me just get that back here so I can make sure I'm not missing any questions you guys have. Okay, so we have this section now that lets us actually call the methods for that smart contract. So if I click on this deposit method, for example, you can see that the same description that we provided in the JS docs of the actual smart contract, you can find here. So again, this is just a really nice way of making it easy for other people to interact with your method. Here's a description of the method. Here it lays out the different arguments that you can provide to the method. So what we're going to do is we're going to actually try to deposit some funds to the personal bank contract. So if I hit, actually, I know that I need to provide the application's account address ahead of time. So I'm going to go ahead and click this right here to copy that to my clipboard. And if I hit call, it brings up this transaction builder, whereas most of the information filled in for us. So we're calling application with ID of 1190. We're calling the deposit method. It's going to be a standard transaction or a standard application call transaction. The sender is going to be the account that we're currently connected with. We want to set the fee automatically, et cetera, et cetera. If we want, we can add an optional note right here. So depositing some algo, we're going to hit add. So now it set up this sort of transaction group. So you can see here is the application call that we just set up. But if you remember going back to the application, it requires the deposit method requires this payment transaction as an argument to the deposit method, right? So this payment transaction is how we're going to actually specify the amount of algo that we deposit to the contract. And so Laura is smart enough to know that that is required as a method argument to the deposit method. So it gives us the option here of filling in that argument. And again, it's setting up most of the parameters for us. It knows that it needs to be a payment transaction. The sender is going to be the account that we're currently connected to. The receiver, we do need to specify manually. So that is going to be the application's account. So we are going to be depositing, let's say, 100 algo to the application's account within this payment transaction. So if we hit add, it should add that in here. And then if we hit simulate, so if we hit simulate, the transaction fails. And why is that? Well, if you remember going back to the resources section of smart contract, where we said that whenever your smart contract has to reference a resource ahead of time, or has to reference a resource on chain, you have to specify that resource ahead of time. You have to specify it when you are calling the method. So in this case, we are actually calling a box, so that the smart contract has to have access to the smart contract box, and that is a resource type that you have to specify ahead of time. And you can see here that this reference array is actually blank, so we're not providing it, and that's why the transaction is failing. But in Laura, if you hit populate resources, it'll just automatically populate that for you. So here it's giving the application ID, and then it's giving the name of the box as base 64. And now if we hit send, it should actually work. I'm going to default password. If we hit send, now we've actually deposited to the smart contract. So like we saw when Brian was walking you through the code, we have this sort of transaction visualizer. Here's the two transaction IDs. This transaction ID is just the actual app call to the deposit method. And then this transaction ID is the actual payment where we're depositing 100 algo to the smart contract account. I believe we can see the note in this transaction. Yeah, so here's the note that we specified in transaction builder. And that's how you call the deposit method. I will pause here. I don't know if, Brian, should I take just another couple minutes to walk through the withdraw method, or should we like move on?
Either way, we can also we can touch on the withdrawal method in the testing if you want.
Oh, sure. Yeah, let's do it that way. Yeah, so I think we'll walk through the withdrawal method, but it's basically the same thing. You can just open this up here and then create this call button, and then you can set up the transaction to basically get your funds back. But everything that we walk through here with the this deposit method, we'll do it similarly with the withdraw method. And yeah, so that's pretty much it for the smart contract section. Just to briefly recap, we talked about some of the fundamental concepts of Algorand smart contracts. We talked about accounts, how every smart contract has its own account that can hold both algo and ASAs. We talked about inner transactions. So smart contracts on Algorand can actually send and receive algo to and from their account using inner transactions. We talked about various ways to store data on the blockchain or on your smart contract using local storage, global storage, and box storage. And in this smart contract, we actually had a demonstration of using box storage to kind of keep track of your depositors. So who deposited what on this contract. And yeah, step through some of the code, the Typescript code, and then we built it, deployed it, and then used LoRa to create an app interface and interact with it on chain. And so that's pretty much it. I think in this next section, well, we're going to take a quick 10-minute break. And then in this next section, Brian's going to walk you through testing this contract. So making sure that everything works exactly as it should before you deploy it. And if you already have this project set up, then the testing files that we're going to be looking at are these two right here. We have the integration test file. And
no spoilers
here. Just a quick spoiler. Just more of a teaser. We're going to be looking at this file. But that's all I'll say.
Storm of Thunder.
I don't want to steal your thunder, Brian. But yeah, so that's what we'll be looking at here in the next section. And yeah, so it's 4 past the hour. So we'll meet back here at 14 past the hour. And in the meantime, feel free to hang out and chat and ask any questions, and we'll do our best to answer them. All right, everyone. Let me pull up the break slide here. I seem to keep losing. Let's see.
You had one question. I don't know if you covered this. Why was the return 101A?
Okay, let me check here. Why the return was 101 algo in the deposit? The return should be 100 algo. If we deposit 100 algo, when we withdraw it, we should get the same amount back. Maybe I'm misunderstanding your question, though. Let me know if I'm misunderstanding that, or maybe you have something else going on. Okay, let me know if I can clarify that. But yeah, if you deposit 100 algo, you should get 100 algo back. Seeing a couple of questions here about what I see one about ARC56. Brian already answered that one.
So there is a question that we can address. So the question from Thomas is, smart contract source code are not public/open source? Well, no, unless someone makes it so. The chain will contain the bytecode of the contract, and that can be disassembled into teal. But that's as far as you can go, really. There's nothing on the public blockchain that has the high-level Typescript that was used as source code to build this smart contract. And so, therefore, it is going to be very, very difficult to create like an ARC56 JSON specification file just based on what's on the chain. However, you can handwrite this stuff. If you take a look through the teal, you can probably figure out what the method names are and the arguments that they take with a little bit of effort if you wanted to create a spec for someone else's closed source contract. But there's no way to like go straight from teal to an ARC56 JSON, unfortunately.
Yeah, so this is the teal that Brian was talking about. So this is the language that's sort of interpreted by the AVM or rather that's used to generate the bytecode that is interpreted by the AVM. You can see it gets quite complex. It's very hard to read. So definitely the preference is to write these smart contracts in TypeScript or Python. And then if you want people to be able to really parse through the logic, you'd want to publish them. You'd want to publish the actual TypeScript code. Okay, cool. All right, well, we'll take a quick 10-minute break, and then when we come back, we will do the testing section.
All right, 317 where I am. Come down the home stretch here. This is the last segment. It's actually 2 short segments. So first we're going to talk about smart contract testing. I'm going to go through unit and integration testing. I'll show you some tools we have for that. And then at the end, we have some additional resources to share, and we'll take some questions. So let's get into smart contract testing. We'll do a few slides, go over some concepts, and then I'll show you how it works in the code. So we got 2 types of testing for which we've got tooling and examples. The first is unit testing. And this is perhaps the more interesting type of testing in the context of AlgoKit. And the other type is integration testing. The essential difference is that unit testing is, oh, sorry, I didn't turn my video on. Unit testing is using an emulated Algorand or virtual machine. It's not hitting an actual network. Whereas integration testing would be actually communicating with a network through a node. So unit testing is intended to be used for narrow testing of contract logic that you've written, and it takes advantage of a library that we have for Algorand Typescript smart contracts. We also have it for Python. And you can test most things that you would normally test against a network. But because there's no network round trip involved, no networking, over the wire, you can run these tests extremely quickly. Integration tests, on the other hand, are actually going to hit LocalNet or testnet and go through the real AVM with full transaction groups and all of the evaluation that happens in mainnet. So let's talk a little bit about unit testing. So in AlgoKit, we've created this AVM emulator, and that it is accessible through this test context, or what you would see as the test execution context. And basically, it gives you access to the contract that you're testing, the ledger. So this is the state of the chain, and transaction groups and results, as well as a utility called any to generate random test data for putting any arbitrary values through your logic. There's also some stub implementations. So, excuse me, you get native implementations of cryptographic functions like the SHA-256. In other cases, you get an emulation within your testing context of things like box storage manipulation. And then finally, there are some things that are not implemented, but they can be mocked or patched in, like API calls. But you can cover a lot of ground in unit testing using this library and cover like the core logic of your application and make sure that all the methods you've written do what they're supposed to do. So in the project that we've been working on, we have some unit tests that are written. There's a deposit test sort of described here, and we'll see the code in a moment. And it follows, in both cases here, we've set it up in such a way to model the arrange, act, assert pattern of testing, which is generally good practice when writing tests. So you're setting up some kind of context, in this case, deploying a contract, getting info, generating a deposit amount, and then creating a payment transaction with that deposit to the app. And then the act phase of testing actually calls the deposit method on the contract with the payment in as an argument to the method call. And then the assert phase is checking that the output that we got from calling the deposit method is what we expected, the original deposit amount. And there's some CLI commands that you can use here in this project. We've got it set up to use AlgoKit project run test dash dash, and then you would put the path to your test file. Same sort of thing is implemented for the withdrawal test, which is essentially a repetition of what we just saw for the deposit test. So let's do a quick quiz. Question is, how does AlgoKit Python or TypeScript unit testing accelerate smart contract testing?
Pulling it up here in just a second. I wish there was a search field on these polls.
I know. I have a conversation going now with the relationship manager at Livestorm about some enhancement ideas.
Yeah, this would be definitely a nice one to have.
Mm-hmm.
Oh, here it is.
So when using our unit testing library, how does that make your testing faster? Does it speed up the local net block time? Does it parallelize the tests on local net? Does it use an emulated AVM without a network? Or does it use dev mode for instant blocks? Let's see. Most people honing in on the emulated AVM. One person thinks it might be dev mode. Let's give it one more second. And most of you are correct. So because it uses an emulated AVM and doesn't actually communicate with any network, local net or otherwise, it significantly accelerates the round trip time of any test. It can basically run at the speed of your computer's memory rather than having to deal with a Docker container and network round trips and all that. Cool, good stuff. Keep going. So on the other hand, once you have completed unit testing for the core logic of your contract, you're going to want to do some integration testing. So broader testing, potentially all the way up to end-to-end testing, where you may have multiple activities strung together. In our personal bank project, we have an example of an integration test. This is similar to what we just saw in the unit testing. It's a deposit method call. Same pattern, range, act, assert, except in this time, we're actually deploying the contract and actually calling the contract, and we're going to use local net for that. So there's real transactions being sent and confirmed, and so forth. I won't dwell too long on this. The withdrawal is the same thing. What is notable here, so if we go back and look at the withdrawal unit test, we did multiple actions where we deposited and then withdrew the deposit, but nothing actually happened on chain. Remember, it's all emulated. But in this integration test, when we do a withdrawal, we are actually sending the transactions for the deposit. Those have to be confirmed, and then subsequently we're calling the withdrawal method, and those transactions have to be confirmed. So we're doing multiple rounds of actual transactions to get this integration test achieved. Cool. So another quick quiz coming at you rapid fire. Integration tests can interact with a local Algorand network. I assume this is a true-false question. Yes. Is that true or false? Let's see. 100% of you said true. Good stuff. Paying attention. I appreciate that. 12 people. Yes, still 100%. Good job, guys. I appreciate you listening. So let's see it in action. I'm back in VS Code. I will zoom in a moment, but I'm going to give you a lay of the land here. So in our project, I'm up here in the smart contracts folder, and within the personal bank contract specific directory here, earlier Gabe took us through the contract.algo.ts. This is the actual smart contract that we authored. So I can move this out of the way. And then alongside that, we've included 2 additional files which end in .spec.ts. These are the testing files we're going to go through now. The contract.spec.ts implements the unit testing that we described, and you'll see that it imports the Algorand Typescript testing library. And the second file, contract.integration.spec.ts, is the integration test, which we just talked about. And you see there's a lot more going on here because we are actually interacting with the chain. So there's a lot more imported. So first we'll start with unit testing. We'll step through how that works. Then we'll do the integration testing and talk through that as well. And I've actually, and then we'll go ahead and run those tests and see the output. So we'll start with our unit testing. Let's move some stuff out of the way here. Make this nice and big. Shout at me if that's not visible. That should be good. So one of the first things you will notice is that we are setting this up just like you would set up other JavaScript or TypeScript testing. We're using vtest. I like to call it vtest. And I think we might be at the point now where that has parity with the API of Jest. So if you're familiar with Jest, you can very easily move to vtest. You can set this up with Jest as well if you want. But the patterns that you see in constructing the test should be familiar to you if you have done testing in other contexts in web or Node.js development generally. So we have a very simple structure here. We describe our personal bank contract, and then within this closure, we basically have 2 tests. The first, it deposits into the contract, and we see the same 3-step testing framework applied. So first we're arranging, and we use this context object, right? So remember I said that we expose this test execution context object. So that's where we start. So we get one, we call it context, and then we go in and we get through the method chaining. We do a .contract and a .create, and we feed it the personal bank contract class. Right? If you remember, the smart contract in TypeScript is implemented as a class. So we pass that class into the create method here, and we basically get a contract that we can play with in the context of this unit testing. So then we're going to go ahead and get an application. So this time we go into the context and we do a .ledger, and we're going to get an application for that contract. So this time we're taking the contract code in the abstract, and we're getting a specific application to test with. So we go ahead and feed in the contract that we just created into this get application for contract method. We get an app. Then we're going to use that utility that we talked about to do some arbitrary deposit. So we do context.any, and one of the things that any exposes is a uint64 random generator, essentially. So our deposit amount is just any arbitrary uint64, and then we're going to build a transaction using this. So the deposit transaction will again do a context.any. Doesn't really matter at this point. We are just creating a transaction in this case, which will be a payment. So we chain that together, .any, .transaction, which will generate a transaction for us, and it'll be a payment. And we're going to be sending it to the application address. So the specific instance of the smart contract application, and the amount, we're going to go ahead and use that randomly generated deposit amount. So we're ready to act now. So in the act phase, we go ahead and do a contract.deposit. So remember the contract is a class. We're basically calling the deposit method of the class in the high-level TypeScript and feeding in the deposit transaction we just constructed above as an argument to the deposit method. And once we have done that, we're ready to assert. So here you can see we are expecting that the output that we got when we acted, we're doing a value of on that, so we get the actual value underneath, to be the deposit amount that we generated randomly in line 11. We do another value of. So we're basically doing a direct comparison of the output of the deposit method call to the value of the deposit amount that we generated for the test. If that passes, test is happy. Very quickly, the withdraw method test is very similar, so that this time it withdraws from the contract. Do similar arrangement. That's all the same. This time when we're acting, we've added a step. So first we are depositing and then subsequently withdrawing from the contract what we deposited just above. And this time we are expecting the output, which is the return from our withdraw method, the value of that to be the value of the deposit amount that was originally put in. So this is like a little bit of an end-to-end test in a way implemented through our emulated AVM using Algorand TypeScript testing. So no transactions actually got sent anywhere, but we can see how that works. Alternatively, when we get into integration testing, you will see the same actions, but in this file, we're actually sending transactions to localnet. So this time we have a little, I'm sorry, tangled in my cord. Okay. This time we are getting a localnet from an Algorand fixture that's provided by Utils. And this allows us to reuse this fixture for testing. So it's a helper that we provide here. And then before we do any of these tests, we use a before all. And what we do is we configure AlgoKit Utils. So this config.configure is basically telling AlgoKit that we're going to be doing some debugging here. And so additional information will be gathered. And we also register some event handlers. So in this case, when you are in the process of debugging, there will be detailed transaction traces to see how they were evaluated, and source maps from the teal back to the high-level language that you can actually debug in the high-level language step by step. And then there's one more little bit of setup here. Well, a little bit more. So we do a before each, so that prior to each test executing, we use that localnet fixture we created up above, and we get a new scope. So it basically cleans a few things up and enables these tests to run in a more isolated way. Lastly, before we're ready to do some testing, remember we're going to be on a real network in integration testing, so we need to deploy our contract. So what's happening here is we are using a factory. So that local net context, we do a little .algorand to get the Algorand client. Remember that from the third segment, second and third segments. And then you do a little .client.get typed app factory. So this is basically where you don't have a deployed instance of a smart contract. And so you need to create one. So you use a factory to do that. So you pass in the factory. So this is a generated class from the smart contract. And then we're going to set the default sender and signer to this account that we're passing into the deploy function. And then we see down here, if you take your factory and do a .deploy on it, you'll get back an app client that can then interact with a specific instance of the deployed application. And then one more bit of context in the .deploy, you can see we're passing in a few options in this object here. So there's some settings for how the deploy can work. This .deploy has a whole bunch of configurability built into it. It's beyond the scope of this course today, but you can play around with it and essentially customize how you want the deployment to behave. And one key way that that can be configured is if you're developing your contract and changing the code and sort of deploying it repeatedly, this controls how the deploy should behave after you've changed the code. So if you set it to fail and the code has changed, then you get an error. If you set it to update, then it updates the same app in place with new code. Replace would delete the old app and create a new one, and then append would just deploy a brand new app and ignore any previous deployment. So depending on how much of a trail you want to leave behind or how you want that to work, this deploy helper can be configured a bunch of different ways. All right, so now we're ready to test. Collapse some of this stuff up here a little bit. So let's do our deposit test first. Excuse me. And in our deposit test, there's a few things happening. So we get a test account and our Algorand client from that local net context, and then the client that we're going to use to interact with our smart contract is retrieved from the deploy function that we just walked through. So we created this deploy function, and we go ahead and call it within this test. To complete a deposit, we have to build a payment transaction like we saw before. So we do this just like we did in section 2, a little Algorand.create transaction.payment. Notice the difference though is we didn't send the payment right away. We just create it and use it as an argument to the method call. So then we take our app client and we do a .send.deposit. We're calling the deposit method, and we pass in the arguments object here, the pay transaction as an argument to deposit. And the last little bit of magic is we say we want to populate all the app call resources. Actually, I think this defaults to true in the most recent version of Utils. You probably don't have to specify this anymore if you're starting fresh, but this makes sure that all of the resources that Gabe taught us about are automatically figured out for you, and you don't have to worry about passing them in manually to construct your method call. And then finally, our test culminates with an expect. So we get the return value from our result of calling the deposit method, and we expect it to be the one algo amount that we paid in when we made the deposit, right? So our payment was an algo amount, algos for one, so one whole algo, and then down here the return is in terms of micro algos. So we're doing a direct comparison to the big int 1 million. Cool. The withdrawal test is, withdrawal test is essentially the same thing, except we had the additional step. We did all the setup, and then we did the deposit first, and then constructed a withdrawal method call. So this time we're doing a client.send. We call the withdrawal method. We see the parameters that are necessary for that. In this case, no arguments are required. And we do pass in a parameter here called cover app call inner transaction fees true. And this is another helper abstraction where the withdrawal method is going to require an inner transaction from the smart contract, but we've hard-coded our smart contract not to pay fees on withdrawal inner transaction. So if we go back over here, we can see when you call the withdrawal method, the inner transaction is set up with a fee set to 0. So when we do this integration test, in order to successfully call the withdrawal method, we got to cover the fees through fee pooling across the atomic transaction group, and that includes inners. And so this helper is going to first simulate the call and then see what inner transactions are required and go ahead and cover them by increasing the app calls transaction fee accordingly. But to put a bound on that, we also pass this max fee parameter. So we don't want this to be an unbound fee coverage. So we pass in a little protection there and put a limit on the amount of fees that the app call can cover for inners. And then at the end, just expect the return value. Same thing. Return, we get that big int back, and we expect it to be equal to the micro algos that we originally deposited. And there you have it. So there's a little bit of magic going on here. This is fairly dense code. Definitely recommend going through this and stepping through it on your own to see how some of these things work. There's a lot going on under the hood that we hope abstracts away a lot of stuff from you as a developer, so you can really focus on your business logic. So let's take a look at what this test produces. And so in the scripts in our project, there is a test script that you can use in addition to the CLI commands. Okay, project run. And I'm going to go ahead and pop that. And then a whole bunch of stuff's going to happen. I'm going to zoom out one notch. Hopefully it's not too tiny for you. And I'll show the output of these tests. So along the way, you can see some information that comes through standard out and tells you a little bit about what's going on here. So it's a slightly low contrast here, but you can see in the contract.spec.ts, this is our unit testing. We are depositing funds into the contract, and you can see the output. This was a random amount, and the output matches the deposit amount, so that test was happy. Same thing with withdrawal. Then here, the next one is the integration test. So you can see it's coming from a different file. And in this case, it was the deposit test. And because in the integration tests, we're actually communicating with LocalNet, we get real transaction IDs, and they are printed to standard out here. And then when we get into deposit and withdrawal tests, see some more output. We're not going to go through it all. And then all the way down to the withdrawal call in the very last integration test. And then we get our summary. So you can see both of the files that were in scope here, both in the integration and the unit testing file. I had a couple of tests apiece. It ran in 2 seconds, 2 files, 4 tests, and you get a nice little coverage report as well. So this should be relatively familiar to you as output if you've used VDIST in other contexts. Here, we used it to run multiple files containing multiple tests each against both an emulated AVM in our unit tests using the Algorand Typescript testing library, as well as against LocalNet with real transactions through a more traditional integration test in both cases, following our arrange, act, assert pattern. And that's essentially it. I'm going to go ahead and speed through our last little section. We just have a couple more things for you. Back to the slides. So throughout this workshop, you have learned about Algorand fundamental concepts, how counts, ASAs, algos, transactions, minimum balance, fees, things like that work. We introduce you to AlgoKit in code in the Utils library, first to do basic stuff, and then all the way up to writing a smart contract and testing it in multiple ways. And we use that personal bank example as a teaching toy example. And we would love for you to continue your learning after this workshop. There's a set of resources here. Our AlgoKit homepage is a great entry point to get to all sorts of things. Our developer portal is our technical documentation. We just rebuilt this at the end of March. It's basically brand new. We put a lot of effort and love into that, and I would highly recommend taking a read through as a human. And also, we have an AI chatbot in there you can ask questions to. We saw Laura throughout. Have a play around. It's a very powerful tool for various things. I saw somebody talking about getting funds out of AlgoFi. Laura's ability to build arbitrary transactions is super useful in those weird situations. The personal bank app example that we went through is available on GitHub. And then we also have what we call the digital marketplace. This is currently in Python. We're going to be porting it over to Puya TS for TypeScript pretty soon. But we've created it as a more complex example. As you can see, a production grade contract. And there's a lot more that goes into that, but it's a bit much to go through in an introductory workshop. Another really good one is when you start to build the front end for your application, there's an amazing community library called Use Wallet created by Doug over at Transaction Lab. And this basically abstracts away having to integrate with a bunch of different wallets and gives you a standard interface. It's the gold standard for building wallet integration on Algorand. Please use it. And finally, we mentioned our Discord server at the beginning. This is the place to go for developer chat socially or to get code help. It is the largest single community of Algorand developers in the world. And there's all sorts of stuff going on in there. The DevRel team is in there. Our engineers are in there. The Algorand Technologies engineers are in there. So it's really the place to be. So introduce yourself, and if you run into issues in your code, you can ask for help and have help. We do have homework for you. It's optional, but if you complete it, we would be honored to give you a certificate of completion, and we'll also be giving away some prizes to be determined. So if you take a little bit of time on your own to deploy your app to Algorand testnet, go ahead and publish that on GitHub, put your GitHub handle in the box for your app using box storage, and then and put your deployed app ID in your GitHub or public GitHub repo, and follow these instructions and submit it through the form. We would be thrilled to offer you a certificate. It's an NFT, but it's also a credential, and it uses some pretty cool stuff by Plausible, and you can put it on your LinkedIn profile if you want. So it's like pretty legit, and the homework will not take you long. So I would encourage you to give it a whirl. All right. Thank you, Gabe. Thanks, everybody.
Thank you, Brian. Thank you, everyone.
Close it out. Bye-bye.
Cheers. Bye-bye.